In the Airframe Structures series of lessons, we will define the various loads applied to aircraft structures, looking at the design and construction of the fuselage, wings, and tail unit. We will examine the materials used in construction and the effects of corrosion and fatigue on these materials. We will discuss the effects of a hard landing on the airframe, and we will review failure statistics and their importance in safe aircraft design. In this first lesson, we will discuss the various loads applied to aircraft structures, both on the ground and in flight. We will examine the effect of fatigue on structures and discuss the methods used to mitigate these effects. A tensile load is one which tends to stretch a structural member. The member is then said to be under tension. Components designed to resist tensile loads are known as ties. Good examples of ties are the stringers, which in modern aircraft take the tensile loads produced in the fuselage structure by pressurization. Compressive loads are the opposite of tensile loads and tend to shorten structural members. Members subject to compressive loads are said to be under compression. Components designed to resist compressive loads are known as struts. You will find numerous examples of struts in an aircraft landing gear, the primary one being the Pneumatic strut, which takes the compressive loads on landing. This will be fully explained in the landing gear lesson. Shear is a force which tends to slide one face of the material over an adjacent face. Riveted joints are designed to resist shear forces. Rivets are being used in this picture to fasten the fuselage skin to the frame. In modern aircraft, they are being replaced by adhesive bonding processes. To review tensile, compressive or shear loads, click one of the three buttons. Most loads to which aircraft components are subjected are a combination of two or all three of these basic loads. Bending of the structure involves the three basic loadings. They are tension as the outer edges stretch, compression as the inner edges squeeze together, and shear across the structure as the forces try to split it. Torsion or twisting forces produce tension at their outer edge, compression in the center, and shear forces across the structure. Buckling occurs to thin sheet materials when they are subjected to end loads, and to ties if subjected to compressive forces. To review bending, torsion, or buckling, click one of the three buttons. Stress is the internal force inside a structural member which resists an externally applied force, and therefore a tensile load or force will set up a tensile stress. Under compressive load, compressive stress. Stress is defined as the force per unit area and is measured in newtons per square millimeter or meganewtons per square meter. When an external force of sufficient magnitude acts on a structure, the structural dimensions change. This change is known as strain. Strain is measured as a ratio of the change in a material's length to its original length, and is a measure of the deformation of any loaded structure. In our extreme example shown here, the original length of the material is 2 meters. When a tensile load is applied, its length increases to 2.5 meters. This gives it an increase in length of 0.5 meters. Therefore, the strain being felt by this material is 0.5 divided by 2, which is 0.25. The 18th century English physicist Thomas Young discovered that the relationship between stress and strain for an elastic material within the elastic limit of the material is generally a constant. This constant is therefore known as Young's modulus of elasticity. Aircraft components are subjected to some or all of these stresses, and they will tend to elongate, compress, bend, shear and twist the component. However, provided the deformation is within the elastic limit of the material, the component will return to its original dimension once the stress has been removed. If any load takes the structure beyond its elastic limit, then the deformation will be permanent. The maximum load that a designer would expect an airframe or component to experience in service is termed the design limit load. This load is defined as a load factor. Load factor is the ratio of the lift of an aircraft to the weight of the aircraft. The load factor is expressed in multiples of g. In straight and level flight, lift is equal to weight, so the ratio of lift to weight is 1, and the load factor is 1g. The design limit load is 2.5g for public transport aeroplanes. The design limit load is 3.4 to 3.8g for utility aircraft and 6g for aerobatic aircraft. The design ultimate load is the design limit load multiplied by a safety factor. The minimum safety factor specified in design requirements is 1.5. The structure must withstand its design ultimate load without collapse. The safety factor is the ratio of the design ultimate load to the design limit load. The aircraft manufacturer will attempt to design an aircraft to take into account all the loads that it may experience in flight. There are various guidelines, formula, and experience to help them in the design of good, fail-safe, and damage-tolerant structures. The designer will take into account the anticipated role of the aircraft. So, for instance, aircraft designed for long-haul operations should not be used for short-haul, as the extra takeoffs and landings will not have been accounted for in the airframe's anticipated fatigue life calculations. The safe life of an aircraft structure is defined as the minimum life during which it is known that no catastrophic failure will occur. All critical components have a safe life, which may be measured in flying hours, landings, pressurization cycles, or even on a calendar basis. After the permitted safe life count has been reached, the relevant item is replaced or overhauled. During the operational life of the aircraft, to minimize the effects of metal fatigue, aircraft designers apply the principles of fail-safe or damage-tolerant construction. A fail-safe structure is based on the principle of component redundancy. It has multiple load paths in parallel, which means that the loads are shared by adjacent members. Therefore, If one part fails, the load will be carried by the adjacent member for a limited period. This must be until at least the next periodic inspection. The disadvantage of dualing the load paths is that it is very expensive in terms of weight, as each of the members has to be strong enough to do the work for both. It is now only normally used for wing and stabilizer attachment points. The bracing struts between the wings and the fuselage of the short Skyvan, for instance, are each made up of 3 members. This design philosophy must be accompanied by a maintenance program to ensure that failures are detected before they progress too far. To gain access to vulnerable areas, a certain amount of dismantling is usually required, although non-destructive testing may be used in less critical areas. Modern concepts of aircraft design employ the stressed skin style of construction, where each piece of the airframe, including the stressed skin, plays its part in spreading loads throughout the entire airframe and is tolerant to a certain amount of damage. These damage-tolerant structures eliminate the extra structural members needed in a fail-safe design by spreading the loading of a particular structure over a larger area. Damage-tolerant structures are designed to withstand a certain amount of damage, which again should be detected during the normal inspection cycle before a failure occurs. A structure which is subject to continual reversals of loading, such as the landing gear or the fuselage of a pressurized aircraft, will fail at a load of less than would be the case for a steadily applied load. This is known as fatigue. The failure load level will depend on the number of reversals experienced. In high-cycle fatigue situations, a material performance can be graphically characterized by an SN curve, also known as a Wöhler curve. This is a graph of the magnitude of the cycle stress, S, against a logarithmic scale of cycles to failure, N. It can be seen that after 100 cycles, at 80% of the ultimate stress, the specimen will fail. But if the stress is reduced to 30% of the ultimate, then the component will fail after 10,000 cycles. A method of locating components on the aircraft must be established in order that maintenance and repairs can be carried out. This is achieved by using reference lines to identify positions fore and aft, left and right, and from top to bottom. Fuselage station numbers are determined by reference to a zero datum line, which is at or near the nose of the aircraft. On some aircraft, such as the one shown here, it is forward of the nose. Station numbers are identified in inches or millimeters forward or aft of the zero datum. Stations forward of the datum are identified with a minus sign, and aft with a plus sign, or no sign at all. In this installation, they are all aft of the datum, so no sign is used. Wing station numbers are measured in inches left or right of the aircraft centerline. Vertical position is identified from the horizontal datum. These positions are known as waterlines or buttock lines and are measured in inches from the datum. Plus is used for locations above and minus for locations below the datum. In this example, the datum is at the bottom of the extended landing gear. The fuselage is the main structure of the aircraft. It carries the aircraft payload, be it passengers or freight, as well as the crew in safe, comfortable conditions. It also provides the crew with an effective position for operating the aircraft and space for controls, accessories, and other equipment. The fuselage transfers loads to and from the wings, tailplane, fin, landing gear, and in some configurations the engines. Modern aircraft fuselages are pressurized, and these pressurized aircraft structures must also be capable of withstanding axial and hoop stresses imposed by the pressurization forces. Axial or longitudinal stresses are set up in the fuselage of aircraft when pressurized, and tend to elongate the fuselage between the front and rear pressure bulkheads. Hoop or radial stresses, also caused by pressurizing the fuselage, tend to expand the fuselage cross-section area. The hoop or radial stresses are of greater significance than the axial stresses. The differential pressures that set up these stresses can be as high as 65.5 kilonewtons per square meter, or 9.5 pounds per square inch. This is the end of the lesson. You should now know that tensile loads are resisted by ties, that compressive loads are resisted by struts, and the meaning of the terms stress and strain. You should know the meaning of the term Young's modulus of elasticity. And you should also understand the relationship between design limit load and design ultimate load, and the safety factor. You should also know what the design limit load is for various types of aircraft. And finally, you should understand the properties of fail-safe and damage-tolerant structures. In this lesson, we will discuss the construction of aircraft's fuselage, wings, and tailplane. There are three main types of fuselage construction in use. First, there is the truss or framework type, which is generally used for light, non-pressurized aircraft. Then there is monocoque, which is only rarely used. And finally, semi-monocoque, which is in use on most other types of aircraft. The last two types of structure are more generally referred to as stressed skin. The framework or truss consists of light gauge steel tubes welded together to form a space frame of triangular shape to give the most rigid of geometric forms. Each tube carries a specific load, the magnitude of which depends on whether the aircraft is airborne or on the ground. It is a strong, easily constructed, and relatively trouble-free basic structure. The framework is covered by a lightweight aluminium alloy or fabric skin to give an enclosed, aerodynamically efficient load-carrying compartment. Monocoque is a French word meaning a single shell. In a monocoque structure, all the loads are taken by the stressed skin, with just light internal frames or formers to give the required shape. Sandwich construction, which is a honeycomb core with a skin of aluminium alloy or composite material such as glass reinforced plastic or carbon fiber reinforced plastic, can be used to provide rigidity and strength. However, even slight damage to the skin can seriously weaken the structure. To be a true monocoque, the structure would have no apertures in it at all. But for practical purposes, they have to be provided for access and maintenance. The apertures need to be reinforced so that the integrity of the structure is maintained. Once the aircraft doors are closed and all the hatches and access panels are fitted, the fuselage is, to all intents and purposes, a monocoque structure. One of the few examples of monocoque fuselage constructions is the Beech Starship. As aircraft became larger and the air loads greater, the pure monocoque structure was found not to be strong enough. Additional structural members, known as stringers or stiffeners, and longerons are added to run lengthwise along the fuselage, joining the frames together. The light alloy skin is then attached to the frames and stringers by riveting or adhesive bonding. Stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress. Longerons are more substantial than stringers and are fitted where extra strength is needed, such as for the seat rails in passenger aircraft. When cutouts are made to stress skin structures, for example to provide access panels, doors or windows, or when repairs are required to damaged areas, reinforcement in the form of doublers or backing plates is required around the cutout. If the skin is machined from solid metal, then that part around the cutouts is left thicker than the rest to provide the required reinforcement. The flight deck windows fitted to pressurized aircraft must withstand both the loads of pressurization and, because birds also use the sky and are not under air traffic control, they must bear the impact loads from possible bird strikes. To do this, they are constructed from toughened glass panels, attached to each side of a clear vinyl interlayer. Windscreens are surrounded with a rubber seal and attached to the frame by bolts passing through the extended edge of the vinyl interlayer. An electrically conductive coating applied to the inside of the outer glass panel is used to heat the window. This prevents ice from forming and maintains the window's flexibility, making it more able to withstand bird strikes. The shock loading of a bird strike impact is absorbed by the ability of the vinyl interlayer to stretch and deform should the impact be sufficient to shatter the outer glass. The aircraft must be capable of continued safe flight and landing after impact with a 4-pound or 2-kilogram bird when the velocity of the aircraft is equal to its design cruise speed, VC, at sea level, or 0.85 VC at 8,000 feet, whichever is the most critical. In other words, the windscreen must be able to withstand this impact without penetration. The vertical and horizontal angles of the windscreen are specified so that each pilot has a sufficiently extensive, clear and undistorted view to be able to safely perform any maneuvers within the operating range of the aircraft. It is important that the pilot has his seat in the correct position to get a good view forwards and downwards out over the window over the coaming and nose of the aircraft, without restricting his overall view. To help with this, reference eye points are often painted on the flight deck windscreen frame. On some aircraft, an opening window to the side of the windscreen, known as a direct vision or DV window, is provided to enable the pilot to have sufficient visibility to land the aircraft safely should the windscreen become obscured. These windows are also sometimes used as emergency exits. Passenger cabin windows are designed to be fail-safe and normally have 2 panes of acrylic plastic mounted in an airtight rubber seal fitted into a metal window frame. The inner and outer panes are each individually capable of taking the full cabin pressurization load, so if one pane fails, the other will prevent loss of cabin pressure. The wings support the weight of the aircraft in the air, and so must have sufficient strength and stiffness to be able to do this. Their strength and stiffness is determined by the thickness of the wing, with the thickness and type of construction used being dependent on the speed and weight requirements of the aircraft. The types of construction are biplane, braced monoplane, and cantilever monoplane. Very few biplanes fly at more than 200 knots in level flight, so the air loads are low, which means that a truss-type design, which is covered in fabric, is satisfactory. The wing spars, interplane struts, and bracing wires form a lattice girder of great rigidity, which is highly resistant to bending and twisting. Unfortunately, this system also generates a relatively large amount of drag, which accounts for the fact that biplanes fly relatively slowly. In flight, the flying wires hold the wingtips down and support the fuselage. On the ground, tension in the landing wires supports the wings. In the braced monoplane type of design, the wing is connected by a brace to the fuselage or landing gear. In flight, the brace is subject to tensile loads and acts as a tie. On the ground, it is under compression and acts as a strut. To provide fail-safe protection, the brace is often made from more than one member. The Shorts Skyvan, for instance, has 3 members per brace. This type of design is mainly used on low-speed aircraft. Now we will look at cantilever wings, the design used by most modern airliners. The wings have to absorb the stresses due to the lift and drag in flight, and, if of this design, their weight when on the ground. This is achieved by building the wing around one or more main load-bearing members known as spars. The wing spars pass from wingtip to wingtip either as single structures or as connected sections. The spar will normally be an I-beam either manufactured as a single part or made up of 2 or more parts to give it fail-safe characteristics. These are constructed so that they will absorb the downward bending stresses when on the ground and the upwards, rearwards and twisting stresses when in flight. In flight, bending stress relief is provided by mounting engines on the wing and by locating the major fuel tanks in the wing. Fuel usage procedures are designed so that the wing tank fuel is used last. This is of particular importance at high all-up weights when the outer wing fuel tanks should be full. As fuel is used, the weight of the aircraft decreases, which reduces lift required and therefore the wing bending moment. The wing may be of a single spar, twin or multi-spar construction. A conventional structure would consist of front and rear spars, stringers, and ribs, with the metal skin attached to them to form a torsion box. The torsion box functions as a beam, but is considerably lighter than a solid beam of the same size, without losing much strength. The stressed skin takes the loads due to the differences in air pressure and the mass and inertia of the fuel in the wing tanks. It generates direct stresses in a span-wise direction as a response to bending moments, and it also reacts against twisting forces. Stringers are span-wise members which give the wing rigidity by stiffening the skin in compression. In most modern aircraft, they are formed by machining integral ridges into the skin. Ribs maintain the aerofoil shape of the wing, support the spars, stringers, and skin against buckling, and pass concentrated loads from the engines, landing gear, and control surfaces into the skin and spars. Ribs often have lightning holes cut into them. As well as reducing the weight of the structure, these holes are usually flanged to help stiffen the rib. The major structural components of the wing are generally manufactured from aluminium alloys. With composite material, such as glass-reinforced plastic or carbon-reinforced plastic and honeycomb structures, being used for more lightly loaded structures. Carbon-reinforced plastics are gaining wider acceptance for the manufacture of major structural components, such as the fin and horizontal stabilizer. There are a number of aircraft mass limitations that you must become familiar with. The maximum zero fuel mass of an airplane is defined as the maximum permissible mass of an airplane with no usable fuel. This limit is set by the maximum bending load that the wing root is able to support. The maximum zero fuel mass sets the maximum load that can be carried in the fuselage. Fuel added to the wing will not increase the wing bending load. In fact, it will reduce it. Maximum structural takeoff mass is the maximum permissible total airplane mass at the start of the takeoff run. Maximum structural taxi mass is the maximum mass of the airplane at the commencement of taxi. This is sometimes also referred to as the maximum ramp mass. Maximum structural landing mass is the maximum permissible total airplane mass on landing in normal circumstances. The tail unit, which is sometimes called the empennage, comes in many different designs. It can be conventional, T-tail, H-tail, or V-tail. The tail unit provides, in most cases, the longitudinal and directional stability and control. A small number of aircraft have their longitudinal stability and control provided by foreplanes or canards, as seen here on the Rutten Cozy. The horizontal surfaces, which are known as the tailplane or horizontal stabilizer, provide longitudinal stability by generating upwards or downwards forces as required. Longitudinal control is provided by either the elevators or the moving tailplane, depending on design. For instance, the Boeing 747 uses elevators for control and the tailplane for pitch trim, whilst on the TriStar the roles are reversed, the tailplane being used for control and the elevators for trimming. The vertical surfaces, the vertical stabilizer or fin, generate sideways forces as required to provide stability about the normal axis. Directional control is provided by the rudder. The operation of these flying controls is fully covered in the Flight Controls series of lessons. Both the tailplane and the fin are subject to similar but smaller bending and torsional stresses as the wing. Structurally, the tail unit components are generally smaller versions of the wings, in that they use spars, ribs, stringers, and skin in their construction. On some aircraft, they may also contain sealed compartments for fuel storage. They are also constructed of the same basic materials as the wings. Usually, aluminium alloys are used, with composites filled with honeycomb structures or high-density expanding foam, sometimes being used for control surfaces to provide greater stiffness at low weight. Aerodynamic flutter is the rapid and uncontrolled oscillation of a flight control, or the surface to which it's attached, which occurs as a result of an unbalanced surface. A full aerodynamic explanation can be found in the Principles of Flight series of lessons. Flutter is caused by the interaction of aerodynamic torsion and bending forces, inertial forces, and the elastic properties of the surface or structure. It can lead to catastrophic failure of the structure. Flutter must not occur within the normal flight operating envelope of the aircraft. Flutter can be prevented by mass balancing control surfaces to alter the moment of inertia of the surface and therefore the period of vibration. This can be achieved by positioning balance weights forward of the control surface hinge line to move the control surface center of gravity closer to the hinge line. Flutter of the wings can be prevented by using the engines as mass balance. This is done by mounting them on pylons forward of the wing leading edge. The fact that an aircraft is poorly maintained, particularly in respect to excessive control surface backlash or flexibility, may mean that flutter will occur at speeds below the limit airspeed. This is the end of the lesson. You should now understand the differences between truss, monocoque, and semi-monocoque fuselage construction, and the differences between biplane, braced monoplane, and cantilever monoplane wing constructions. You should also note the following key points from this lesson. Spars on non-stressed skin wings absorb the downward bending stresses when on the ground, and the upwards, rearwards, and twisting stresses when in flight. On stressed skin wings, they are assisted in this by the skin itself. On larger aircraft, a wing torsion box is often formed from spars, skin, stringers, and ribs. Fuselage stringers stiffen the skin and assist the sheet materials to carry loads along their length. On pressurized aircraft, they take some of the strain caused by the pressurization and convert it into tensile stress.
Flutter can be prevented by mass balancing control surfaces. Finally, you should know the meaning of the various maximum structural masses to which an aeroplane is limited. Remember that the maximum zero fuel mass of an aircraft limits the bending moment at the wing root, while allowing the maximum load to be carried. In this lesson, we will begin by looking at the materials from which aircraft structures are made, and we will look at the effects of corrosion on these materials. We will also examine the effects of a hard landing on the aircraft structure, and we will look at failure statistics and their effect on flight safety. We will finish the lesson by having a quick look at the maintenance methods employed to keep aircraft in a safe and airworthy condition. Modern aircraft are constructed mainly of aluminium and its alloys, with smaller amounts of steel and titanium for the major structural components. Composite materials are used extensively for more lightly loaded structures. Each material is chosen for its particular properties with regard to the fatigue strength, wear resistance, strength to weight ratio, fire resistance, and so on. Aluminium alloys are the most widely used metals for structural use due to them having a good strength to weight ratio. Duralumin is an aluminium and copper-based alloy which has poor corrosion resistance except when clad with pure aluminium. It has good thermal and electrical conductivity and good fatigue resistance, but it is difficult to weld. Aluminium-clad duralumin is the most popular material in use for airliner skins. Steel and its alloys are relatively heavy, but can be made very strong. They are used only where strength is vital and weight can be ignored, for instance, in undercarriage units. Titanium is much lighter than steel, but it is just as strong and can be used where fire protection is required, for instance in engine firewalls. Titanium has good strength, and it retains this strength and its corrosion resistance up to temperatures of 400 degrees Celsius. It is, however, expensive to produce. The SR-71 Blackbird was the first aircraft to make extensive use of titanium within its structure, paving the way for its use in modern fighter and commercial aircraft. The Boeing 777 uses some 58 tons of titanium in its construction. Magnesium alloys are also used, their principal advantage being weight. Magnesium alloy has an excellent strength to weight ratio, aluminium of the same strength being 1.5 times heavier. Magnesium alloy has poor elastic properties, so its use in primary structures is limited. It is often used in the construction of gearboxes. Composite materials are becoming more and more used in aircraft construction. They are made up from layers of fiber, carbon, glass or Kevlar, molded into the required shape with a hot plastic resin, which is normally epoxy. Carbon fiber reinforced plastic is used where structural strength is required. It can be produced with the same strength as an aluminium alloy, but with a weight saving of about 20%. Glass fiber reinforced plastic does not have the same structural strength, but is often used for fairings and non-load-bearing panels because of its light weight. Kevlar has very low electrical conductivity and high fire resistance. Aircraft cabin doors, overhead bins, and bulkheads may be built with honeycomb cores made up of Kevlar. Composite materials have good resistance to corrosion and can be easily formed into complex shapes, but their fatigue behavior is different to that of conventional metal alloys. Metal structures suffering fatigue retain their design strength up to a critical point, after which failure occurs very rapidly, whereas composites lose their properties gradually. Interest in composites for structural use is due to their high specific strength and specific stiffness allied with their ability to retain these properties at high temperatures. The Airbus A380 uses a significant amount of composite material in its construction. The tailplane, for instance, is almost entirely constructed from carbon fiber reinforced plastic. Corrosion is the slow destruction of metal by electrochemical reaction. It is one of the most persistent defects found in aircraft. Rectification of advanced corrosion has been known to take thousands of man-hours. In fact, more than 10% of engineering downtime is spent in dealing with corrosion problems. It is therefore essential that it is recognized at the earliest possible stage, and that effective preventative measures are taken. When a metal is exposed to the air, oxygen in the air reacts with the bare metal to form an oxide film which adheres to the metal surface. This oxide film forms a barrier between the air and the metal surface, which can protect the underlying metal from further attack. A good example of this is the Statue of Liberty. It is clad in copper. This has developed a green copper oxide coating which protects the metal from the elements. With the exception of oxidation, all other corrosion takes place when the metal is in contact with water, either as a liquid or as water vapor in the atmosphere. Corrosion is mainly electrochemical in character and occurs in conditions that permit the formation of minute electrical cells in or on the attacked metal in the presence of an electrolyte. It will also occur when a difference in potential exists between the different constituents of an alloy, or where dissimilar metals are in contact with each other. The degree of corrosion is proportional to the amount of impurities in the water, the impurities being due to industrial pollution which has high sulfur content, or by airborne salt particles when operating over the sea. The resultant action is that the metal undergoes a chemical change. The attack may extend over the entire surface of the metal, or it may penetrate locally, forming deep pits, or even follow grain boundaries inside the core of the metal. The weakening effect can be aggravated by stresses in the metal due to external loads, or there may be residual stresses from the manufacturing process or method of assembly. The three types of corrosion that we are going to look at are surface corrosion, intergranular corrosion, and stress corrosion. The surface corrosion on ferrous metals, other than stainless steel, can be recognized as a reddish-brown powder, commonly known as rust. The surface of aluminium or magnesium can become covered in white to grey powdery deposits. On magnesium, there may also be deep pitting of the surface. The surface of copper and its alloys may become covered in blue-green salt deposits. Surface corrosion is the least damaging. It is relatively easy to spot so it can be identified and dealt with at an early stage. The microstructure of metals and alloys is made up of crystals or grains, separated by grain boundaries. Intergranular or intercrystalline corrosion is a localized attack along the grain boundaries or immediately adjacent to grain boundaries, while the bulk of the grains remain largely unaffected. It penetrates the core of the metal along the grain boundaries. The rate of attack is not limited by the lack of oxygen and is accelerated if applied or residual stresses are present. Repeated, fluctuating stresses cause separation of the grain boundaries, accelerating the spread of corrosion. As a result, higher stress concentrations can occur in the remaining sound material, thus producing cracks which can spread, leading to component failure. This is a very dangerous form of corrosion, as detection is difficult and serious weakening can occur before any external evidence is visible. The only surface indication may be a series of hairline cracks, probably only visible through a magnifying glass. There is no effective method of determining or of limiting the loss of strength which will occur with this type of corrosion. So when it is detected, the affected part must be immediately rejected. A combination of a steady tensile load and corrosive environmental conditions produce a form of metal fatigue known as stress corrosion cracking. The stresses may be built in during manufacture, introduced during assembly, or may be applied during operation. Metal under stress corrodes more rapidly than unstressed metal. It usually begins with pitting at the surface. This increases the stress at the pit, causing a crack which can extend under the combined action of corrosion and load until failure occurs. There is generally very little evidence of corrosion and no apparent loss of metal. This type of corrosion is often not spotted until a serious failure occurs. An aircraft's landing gear is designed to withstand landings of a particular maximum all-up weight and a maximum vertical descent velocity of 10 feet per second or 3.15 meters per second. If either of these parameters is exceeded during a landing, then the aircraft may be damaged. Damage may also be caused to some aircraft by landing with drift applied, or by touching down with the nose or tail wheel first. Some aircraft are fitted with hard landing indicators, which give a visual indication that specific G-forces have been exceeded. But in all cases, if the crew suspect that a hard landing has been made, then all details, including aircraft weight, fuel distribution, landing speed, rate of descent, and any noises indicative of structural failure, must be reported so that an inspection can be carried out prior to the next takeoff. The damage which may be expected following a hard landing will be concentrated around the landing gear, its supporting structure in the wings and fuselage, around the wing and tailplane attachments, and the engine mounts. Secondary damage may be found on the fuselage skin and structure, depending on the configuration and loading of the aircraft. On some aircraft, it is specified that if no damage is found in the primary areas, then the secondary areas do not need to be inspected. However, the precise inspection requirements vary from aircraft to aircraft, so reference must be made to the appropriate maintenance manual. It is important for pilots to have an understanding of the fail-safe concept and the way it is designed into modern aeroplanes. The following is a summary of the required relationship between component failures, their effect and the possibility of them happening as required by the certification specifications from EASA, as detailed in CS25. Failures are classified into 5 groups, according to the severity of their effects. The lowest class is no safety effect. This is self-explanatory. It will have no effect on the operation of the aeroplane. Next is minor failure. This failure condition will significantly reduce the aeroplane's safety, but the crew's actions required will be well within their capabilities. There may be some physical discomfort to passengers or cabin crew. Third is a major failure. This will lead to a significant reduction in safety margins or functional capabilities, a significant increase in crew workload, possible flight crew discomfort, and possible physical distress, including injury to passengers or cabin crew. A hazardous failure will reduce the capability of the aeroplane or crew to cope to the extent that there will be a large reduction in safety margins. The conditions may cause physical distress to the flight crew so that they are unable to perform their required tasks accurately or completely. There may be serious or fatal injuries to a small number of passengers or cabin crew. Finally, a catastrophic failure will result in multiple fatalities and probable hull loss. Shown here is a summary of the failure classifications. Spend a moment studying it before moving on. The allowable likelihood of a failure occurring is defined in both qualitative and quantitative terms. A probable failure condition is one which is expected to occur one or more times during an aeroplane's lifetime, or less often than once every 1,000 flight hours. A remote failure condition is unlikely to occur to each aeroplane during its life, but it may occur several times when considering the life of a number of aeroplanes of the same type. Or it may occur less often than once every 100,000 flight hours. Extremely remote failure conditions are not expected to occur to each aeroplane, but they may occur a few times when considering the total life of all aeroplanes of the same type. Or they may occur less often than once every 10 million flight hours. Extremely improbable failure conditions are so unlikely that they are not expected to occur during the entire operational life of all aeroplanes of one type, or less often than once every 1,000 million flight hours. The simple rule is that the more severe the outcome of a failure, the less likely must be the possibility of it happening. As you can see from the chart, a catastrophic failure must be extremely improbable, whilst a minor failure may be probable. Spend a moment studying this chart. It shows in a diagrammatic form the required relationship between the probability and severity of failure conditions. As well as obeying the rules about the probability of failure, modern aeroplanes are designed around the fail-safe concept. The basic objectives used to achieve this are that a single failure of any single element of any system or subsystem should be assumed. This failure must not be catastrophic. a second failure in the same system on the same flight should not be catastrophic unless its joint probability with the first failure is extremely improbable. In order to achieve this, the fail-safe design concept uses one or more design principles or techniques to ensure a safe design. Redundancy and backup systems are used to enable continued function after failure of one or more systems. A good example of this is the use of multiple engines. Systems and components are isolated and segregated so that failure of one does not cause failure of another. For instance, aeroplanes are designed with multiple independent hydraulic systems with no transfer of fluid between them. Systems are tested for proven reliability so that multiple independent failures are unlikely to occur on the same flight. Airlines using large twin-engined aeroplanes for extended range operations have to continually monitor and prove their engine reliability in order to be allowed to operate. Failure warning systems are provided for the crew to be made aware of such failures. Flight crew procedures are developed to limit the effect of any failure. A checking system is used to ascertain a component's condition. Components are designed to sustain damage without failing, or to direct the effects of a failure in a way that limits its safety impact. And lastly, components are designed with margins beyond their planned life. On the screen is a summary of the design principles and techniques used to produce fail-safe aeroplanes. Spend a moment studying it before moving on. For aircraft structures and components, there are two maintenance methods in common use. These are known as hard-time maintenance and on-condition maintenance. Hard-time maintenance is a preventative primary maintenance process. It requires that an appliance or part be periodically overhauled in accordance with the company's maintenance manual, or that it be removed from service. An example of this would be a part that must be removed from the aircraft after X amount of flight hours or calendar years for an overhaul, or disposal if it is a non-repairable item. On-condition maintenance is also a preventative primary maintenance process. It requires that an appliance or part be periodically inspected or checked against some appropriate physical standard to determine whether it can continue in service. The purpose of the standard is to remove the unit from service before failure during normal operation occurs. That ends this lesson. You should now be familiar with the various materials used in aircraft construction and the advantages and disadvantages of each material. You should know the causes and effects of corrosion. You should understand the effects of a hard landing. And you should have a good knowledge of what constitutes a fail-safe aircraft design. Finally, you should understand the difference between hard time and on-condition maintenance.
Hydraulics is the science relating to the behaviour of liquids under various conditions. In aircraft, the hydraulic system provides a means of operating large and remote components that it would not be possible to operate satisfactorily by other means. Hydraulic systems provide the power for the operation of components such as landing gear, flaps, flight controls, wheel brakes, and other systems that require high power, accurate control and rapid response rates. In this series of lessons, we will begin by looking at hydraulic theory, including the physical laws that apply to hydraulic systems. We will discuss the properties required of hydraulic fluids. We will look at the components that make up a basic hydraulic system, and we will see how this system can be improved by adding further components. We will examine the controls and indicating systems required to allow the flight crew to operate and monitor the system, and we will examine the components required for ground servicing purposes. Finally, we will look at a typical hydraulic system as fitted to a modern airliner. Bertholli Pascal was a 16th century French mathematician, physicist and religious philosopher. He discovered that if a force is applied to a liquid in a confined space, then the resulting pressure will be felt equally at all points. This fact is therefore known as Pascal's law, and is the principle upon which all hydraulic systems operate. However, before we get involved in Pascal's law, we first need to review some of the units and formulae used to measure pressure, area, force and work. The force acting on a liquid is the total load available and can be measured in newtons, pounds or kilograms. 1 kilogram equals 9.8 newtons or 2.2 pounds. Therefore 1 pound equals 4.45 newtons. Area can be measured in square inches or square metres. There are 1,550 square inches in a square metre. Pressure is force per unit area. It can be measured in pounds per square inch or newtons per square metre. In the example, we have an area 2 metres by 2 metres, 4 square metres. If we apply a force of 16 newtons to this area, then the force felt on each square metre will be 4 newtons. Thus the pressure is 4 newtons per square metre. In theoretical mathematics, the normal units of pressure are newtons per square metre. These units are often referred to as pascals. 1 newton per square metre equals 1 pascal. However, most aircraft gauges are calibrated in pounds per square inch, or psi. It is probably worth noting that a pressure of 1 newton per square metre is very small. It is equivalent to 0.000145 pounds per square inch. So the more commonly used metric units are kilopascals or megapascals, abbreviated to kPa or MPa. Another unit of pressure in use is the bar. You will have used this for altimeter settings. Standard pressure is 1013.2 millibars or 1.0132 bars. 1 bar is equivalent to 100,000 pascals. So in some areas of the world, the barometric pressure is given in hectopascals, 1 millibar being equivalent to 100 pascals, or 1 hectopascal. The work done by a machine can be measured by multiplying the force applied by the distance moved. It is measured in joules, where 1 joule is equal to a force of 1 newton being moved through 1 metre. Work done is a form of energy, so we need to bear in mind that energy, and therefore work, can be neither created nor destroyed. Let us now go back to Pascal's law. Pascal stated that if a force is applied to a liquid in a confined space, then the resulting pressure will be felt equally at all points. If in the diagram the force applied is 10 newtons, and the area of the piston is 0.5 square metres, then the pressure will be 10 divided by 0.5, which equals 20 newtons per square metre, or of course 20 pascals. That pressure will be the same in all areas of the liquid. If we now increase the force to 20 newtons, what will the pressure be? Press continue to see the answer. The answer is 40 newtons per square metre, or 40 pascals. If we go back to our original example, but this time increase the area of the piston to 1 square metre, keeping the force applied at 10 newtons, using the formula pressure equals force divided by area, then the pressure will be 10 divided by 1, or 10 pascals. We can see from these examples that the pressure varies in direct proportion to the force applied on the piston, but in inverse proportion to the piston area. A simple hydraulic system, such as that shown, consists of 2 different sized cylinders connected by a pipe. According to Pascal's law, pressure exerted on the smaller piston is transmitted through the fluid to act on the internal surface of the larger piston. Pressure is a property of the system, not the pistons, and is therefore experienced equally by each piston. Because each piston has a different surface area, the force exerted by each piston will be different, even though the pressure is the same. Although in our example the pistons are close together, this does not need to be the case. The interconnecting pipe can be as long as required, and ignoring friction, it will have no effect on the system. It was this principle that was understood by Joseph Bramah when he patented the Bramah press in 1795. He observed 2 facts about his press. Firstly, the smaller the area under load, then for a given force, the greater will be the pressure generated. And secondly, the larger the area under pressure, the greater will be the load available. In our example, piston A has an area of 0.002 square metres, and we are applying a force of 1000 newtons to it. We know that pressure equals force divided by area, so this will produce a pressure of 1000 divided by 0.002, which equals 500,000 pascals, or 500 kilopascals. According to Pascal, this pressure will be felt throughout the whole system. Piston B has an area of 0.004 square metres. It will therefore be able to support a force of 500,000 multiplied by 0.004, which is 2000 newtons. If we now move piston A down 0.6 metres, then the work done, force multiplied by distance, will be 1000 multiplied by 0.6, which is 600 joules. Ignoring any losses due to friction, the same amount of work must be done on piston B, so it must move up 600 divided by 2000, which is 0.3 metres. We can see from this that for a given system pressure, the force produced will be directly proportional to the piston area, and the distance moved by the piston will be inversely proportional to the piston area. Now try this example for yourself. What will be the force available on piston B? The correct answer is 12,000 newtons. If you answered it correctly, then continue. If not, you may wish to review the lesson so far before carrying on. The Bramah press is a passive hydraulic system. A force is only applied to a piston, piston A in our example, when it is desired to move a load, piston B. Pressure is only generated when it is required. Although this is a very simple system, it can be extremely powerful. In 1846, Robert Stephenson used a single hydraulic press to hoist gigantic 1,144-ton tubes into place for his Britannia Bridge across the Menai Straits, between the island of Anglesey and the mainland of Wales. A smaller example can be found in many light aircraft braking systems. Here, piston A in the press is replaced by the master cylinder, the force being produced by the pilot's foot on the pedal. Piston B is now the slave cylinder. You will notice that we have added a fluid reservoir. This is there purely to keep the system topped up in case of minor leaks. For more complicated aircraft systems, a pump is required to deliver a flow of liquid into the system. It is worth noting that a pump in itself does not supply pressure. If it is pumping through an open-ended tube, then the fluid will have no pressure. In order for pressure to build, the flow has to be restricted. In aircraft hydraulic systems, this restriction is provided by movable pistons, which travel backwards and forwards in cylinders, known as hydraulic jacks or actuators. The power required for operating different services varies according to their size and loading. This can be catered for by using actuators with pistons of different areas for different work as required by the load, whilst keeping the pump output pressure constant. For instance, main undercarriage up jacks will need pistons with a very large surface area, whilst individual spoiler panels will have relatively small pistons. This is the end of the lesson. You should now be familiar with the units of measurement used in hydraulic systems. You should understand Pascal's law and have a complete understanding of the Brahma press, particularly the relationships between force, distance, and area. In this lesson, you will learn of the properties required of aircraft hydraulic fluids, and of the necessity to have well-designed pipelines for carrying the fluid around the system. Plus, we will look at the design of the various seals used in a system to stop the fluid escaping. There are a number of properties that we would ideally like hydraulic fluid to have. Firstly, it is essential that hydraulic fluid is relatively incompressible in its normal pressure range. That is, up to 276 bar or 4000 psi. This will ensure instantaneous operation of the services. In fact, almost all liquids have this property. In the diagram, we show the effect of applying pressure to a container of liquid. When a pressure of 346 bar or 5000 psi, well above normal system operating pressure, is applied, the liquid is compressed by only 1% of its original volume, and 99% remains. Hydraulic fluid must have good lubricating properties for both metal and rubber, as it will be used as the lubricant for all moving parts throughout the system. It should have a viscosity low enough to keep friction to a minimum, but high enough to help prevent leaks. Viscosity is a fluid's resistance to flow. The higher the viscosity, the greater the resistance. The fluid needs to have a high boiling point to help prevent cavitation, and a very low freezing point, as the reservoir may well be outside of the heated fuselage. The minimum required range is plus 80 degrees centigrade to minus 70 degrees centigrade. Cavitation will be explained in a later lesson. Hydraulic fluid should be non-flammable, or have a flash point above 100 degrees centigrade. It should be chemically inert and be non-corrosive. It needs to be resistant to evaporation and have freedom from sludging and foaming. Finally, it should have good storage properties, as well as being reasonably priced and readily available. No current hydraulic fluid has all of these properties. There are two types in common use, both of which are toxic and will damage skin, paintwork, sealing compounds, perspex and such like. Both types of fluid are an irritant. Eyes should be protected from them, and prolonged contact with skin can cause damage. Any contaminated skin should be washed with soap and water immediately. The two types of fluid you are likely to meet are Devstan 91-48 and Skydrol. Devstan 91-48 is a super clean mineral hydraulic fluid. Recommended for all hydraulic systems operating under high pressures and low or very low temperatures, from -54 degrees Celsius to +90 degrees Celsius. It is equivalent to H515 NATO, OM15 Joint Service, and MIL-H-5606F in the United States. It is normally coloured red and is used in hydraulic systems with synthetic neoprene rubber seals. Skydrol is a phosphate ester-based synthetic hydraulic fluid, which is purple in colour. It is used in hydraulic systems containing synthetic butyl rubber seals. Prolonged exposure will damage skin, and eyes must be protected from it. All measures should be taken to avoid skin contact. In the event of a leak, it may spray out as a fine mist, and eye protection must be worn when investigating leaks. If any hydraulic fluid does come into contact with eyes, then they should be rinsed thoroughly with clean water. A medical assistant should be sought. It has a very high flash point of 170 degrees centigrade and is less prone to cavitation than mineral oil type fluid because of its high boiling point. Skydrol is the most dangerous to personnel, but most modern airliners use Skydrol in their hydraulic systems. Both of these fluids are flammable if subject to sufficiently high temperatures and a source of ignition. However, because of its very high flash point, Skydrol is much less so. It is of major importance that only the specified hydraulic fluid, or its approved alternative, is used in a hydraulic system. If the incorrect fluid is added to a system, breakdown of the seals is likely, causing fluid leakage, both internally within components and externally from the actuators. Failure of the seals in the pump could well lead to overheating. Filters may become blocked with debris, and parts may be damaged by corrosion. The colouring of the fluid assists in its identification, and also assists in finding hydraulic leaks. However, it must never be used in isolation to identify a type of fluid. The fluid may not retain its original colour when it has been in use for some time. The specification can only be confirmed by consulting the aircraft manual, and by only using fluid from sealed containers or the appropriate replenishment rig. The efficiency of a hydraulic system is governed by the resistance to motion encountered by the fluid. Force is expended in overcoming static resistance, which is friction in cylinders caused by moving parts, piston rods rubbing against bearings and seals, and by fluid rubbing against the pipe walls. Large bore pipes and frictionless pistons would allow nearly 100% of the force to be utilised, but would incur large weight and cost penalties. Friction between pistons and cylinders, and piston rods and bearings, cannot be completely eliminated. It can only be lessened by good design and workmanship. The friction between the walls of the pipes and the fluid depends upon the velocity of the fluid in the pipes, the length, bore and the internal finish of the pipes, and the number of bends. Good systems are designed with pipe runs being as short, wide and straight as is practicable. Seals perform a very important function in a hydraulic system, their primary purpose being to prevent leakage of fluid. Static seals, gaskets and packing are used in many locations, and these prevent fluid leaks by being squeezed between two non-moving surfaces. Dynamic seals, fitted between sliding surfaces, may be of many different shapes, depending on their use and on the fluid pressures involved. U and V-ring seals are effective in one direction only, but O-rings and square section seals are often used where pressure is applied in either direction. Where high pressures are used, an O-ring is normally fitted with a stiff backing ring, which retains the shape of the seal and prevents it from being squeezed between the two moving surfaces. Dynamic seals require lubrication to remain effective, and wetting of the bearing surface, or a slight seepage from the seals, is normally acceptable. Seals are made in a variety of materials, depending on the type of fluid with which they are to be used. If a seal of an incorrect material is used in a system, the sealing quality will be seriously degraded, and this may lead to failure of the component. Similarly, if the incorrect hydraulic fluid is used, it will almost certainly damage the seals. Seals are easily damaged by grit, and a wiper ring is often installed on actuators to prevent any grit that may be deposited on the piston rod from contaminating the seals. That concludes the lesson on hydraulic fluids. You should now know all the desired properties of a hydraulic fluid. You should also know the properties of and the differences between the two commonly used fluid types, including the differences in colour and the types of seals that each can be used with. In this lesson, you will learn about the components that make up a basic hydraulic system and how the two types of basic system operate. The Brahma press was, as previously mentioned, a passive hydraulic system. However, apart from light aircraft brakes, it is of little practical use to us. Most aircraft hydraulic systems are active systems, where a pump supplies the pressure. There are two types of active hydraulic system in common use. They are known as the open center system and the closed system. There are 6 main components common to both systems: a reservoir of oil, a pump, selector or control valves, an actuator or actuators, filters, and a relief valve. We will begin by explaining how the components of the two basic systems integrate with each other. Then, in later lessons, describe the various components in greater detail. The simplest hydraulic system used in aircraft is the open center system. Its main disadvantage is that only one service can be operated at a time. Fluid flows from the pump, through the pressure filter to the first selector valve. If the service connected to this valve is not operating, then the valve will be in the position shown, and the fluid will flow through the central port to the second selector valve. If this service doesn't require fluid, then this valve will also be in the position as shown, and again the fluid will flow through the central port. This can continue for as many valves as required. When the fluid passes through the last valve in the sequence, it returns to the reservoir. This allows the engine-driven pump to run in an off-loaded condition, as little pressure is generated, but there is still a flow of oil through the pump to cool and lubricate it. On selection of a user system, the fluid is directed to the actuator, which will move. The fluid from the other side of the actuator will return to the reservoir via the central port of the second selector. When the actuator reaches the end of its travel, the selector is returned to neutral in order to offload the pump and allow other services to be selected. The relief valve will relieve excess pressure if the selector is not returned to its neutral position. This type of system is popular in many light aircraft, which do not require a constant pressure to be maintained all the time. Only items such as landing gear and flaps will be powered for short periods of time on each flight. The closed system is used on almost all larger aircraft. Its great advantage being that multiple services can be operated at the same time. Their use is only limited by the volume flow capacity of the pump. With this system, operating pressure is maintained in that part of the system which leads to the selector valves, and some method needs to be used to prevent overloading the pump. In systems which employ a fixed volume constant delivery pump, an automatic cutout valve is fitted to divert pump output to the reservoir when pressure has built up to normal operating pressure. In other systems, a variable volume constant pressure pump is used. This type of pump automatically reduces delivery flow as pressure increases. We will examine both of these pumps in greater detail in the lesson on pumps. This system operates its services in the same way as the open center system. The selector valve is moved, opening up pressure and return lines to the required service. However, there are two important differences. Firstly, as shown here, two or more services can be operated at the same time. And secondly, it is not so important to return the selector valve to neutral once the operation is complete, as the pump control system is designed to deal with the consequent pressure increase. Nonetheless, in most systems, the selector valve is returned to neutral, as this performs the important function of producing what is known as a hydraulic lock across the actuator. What this means is that the fluid is locked in on both sides of the actuator. Consequently, because the fluid is incompressible, the actuator will not be able to produce any undemanded movement. In some simple light aircraft systems, a hydraulic power pack is used. This consists of an electrically driven pump which is controlled by a pressure-operated switch, with an integral reservoir and an accumulator. When the service is selected, pressure will drop, causing the accumulator piston to move up, switching on the pump. The pump will operate until the service reaches its required position, and the accumulator is repressurized, when it will be automatically switched off again. You should now understand the differences between the open center and closed hydraulic systems. Bear in mind that the big advantage of the closed system is that 2 or more services can be operated simultaneously. Whilst in the open center system, you are limited to operating 1 service at a time. You should now also understand the meaning of the term hydraulic lock. In this lesson, we will look at the various types of pumps used in aircraft hydraulic systems. Pumps are used to draw oil from the reservoir and deliver a supply of fluid to the system. Pumps may be hand-operated, engine-driven, EDP, electric motor-driven, pneumatically operated, ATM, driven from a ram air turbine or RAT, or hydraulically operated using a power transfer unit or PTU. The latter 3 pumps, the pneumatically operated pump, the RAT and the PTU, are usually used to provide a backup supply to an engine-driven pump, thus providing hydraulic system redundancy in the event of engine or EDP failure. The output of the ram air turbine will normally be used as a backup solely to operate the primary flight controls and brakes. A hand pump may be the only source of hydraulic power in a light aircraft hydraulic system, but in larger aircraft, hand pumps may be employed to allow ground servicing to take place without the need for engine running, enabling lines and joints to be pressure tested and cargo doors to be operated. The hand pump is usually a double-acting pump, delivering oil on both strokes in a very compact body. It incorporates non-return valves and a relief valve, which can be set to relieve at any required pressure. Typically, this is about 10% above normal system pressure. The piston assembly is connected to the operating handle by the piston rod. In the centre of the piston, there is a transfer valve, which is spring-loaded to the closed position. When the handle is moved up, the piston assembly will move down. This will increase the pressure in the cylinder below the piston and hold NRV1 closed. At the same time, this pressure will be felt on the bottom of the ball in the transfer valve, and it will open, allowing fluid to flow from below to above the piston. As the piston moves down, the volume of fluid displaced from below the piston is greater than the volume available in the cylinder above, because of the presence of the piston rod. This excess fluid will open NRV2 and flow through the outlet. The relief valve will remain closed, as it is set at a higher pressure than NRV2. Once the piston reaches the bottom of its travel, the handle will now be moved in the opposite direction, moving the piston assembly up again. As the piston moves up, the pressure above it will increase. The spring will close the transfer valve, and fluid from above the piston will flow through the outlet. There will be suction felt below the piston, and this will open NRV1, and fluid will flow in from the reservoir. There are 2 types of powered pump in common use. They are the constant delivery fixed volume type and the constant pressure variable volume type. We will look first at the constant delivery fixed volume pump. A typical example of this type of pump is the spur gear displacement pump, shown here. One of the gears is driven by the power source, normally the engine, and this gear in turn drives the other gear. As the 2 gears rotate, fluid is carried around in the spaces between the teeth from the inlet to the outlet side of the pump. This type of pump gives a relatively large flow rate. However, its output pressure is relatively low. It is usually a single, as shown, or double-stage pump. This type of pump supplies fluid at a constant rate, irrespective of demand, and therefore if it is being mechanically driven by the engine in a closed system, it needs an automatic cutout, ACOV, or relief valve, to return the fluid to the reservoir when the actuators have reached the end of their travel and the system is not operating. Operation of the ACOV will be explained later. In order to prevent the ACOV constantly cutting in and out, this type of system also requires an accumulator. Again, the operation of the accumulator will be explained in a later lesson. The constant pressure, variable volume type of pump supplies a variable volume of fluid and controls its own pressure. This type of pump is typically fitted in modern aircraft, whose systems operate at between 3,000 and 4,000 psi. The pump is made up of a number of components. There is a stationary kidney plate, so named because of the two kidney-shaped slots cut in it. The fluid supply from the reservoir enters the pump through one slot, and the pressurized fluid exits by the other. The cylinder block is rotated by whichever source is driving the pump. Cut into this block are a number of cylinders. There is direct metal-to-metal contact between the rotating cylinder block and the stationary kidney plate. This contact is lubricated by hydraulic fluid at system pressure. Each cylinder has a piston fitted into it. The pistons are connected by shoes to the non-rotating yoke or swash plate. Again, lubrication is by hydraulic fluid at system pressure. The angle of the swash plate, and thus the piston stroke, is varied by the position of the control piston. The control piston has pump outlet pressure on one side of it and a spring on the other. With the pump stationary, there will be no hydraulic pressure, so the spring will push the control piston fully to the right, and the swash plate angle will be maximum. The entire assembly is enclosed in a case which is filled with hydraulic fluid, cooling the pump, before it is returned to the reservoir by an independent pipeline. This oil is known as case drain fluid. The condition of the case drain filters are good indicators of the condition of the pump. As the pump starts to rotate, the pistons will ride up and down the angled swash plate, moving in and out of the cylinder block. They are moving out as they pass the inlet kidney-shaped slot, so they suck fluid in. As they move down the other side of the swash plate, they are now being pushed into the cylinder block, forcing fluid out through the pressure slot. As pressure builds up, the control piston will move to the left, reducing the swash plate angle and therefore the pump output. When normal operating pressure is reached, if no surfaces are being operated, the swash plate will be almost vertical, the piston movement will be almost zero, and there will be only a small flow of fluid through the pump. This flow is for pump cooling and lubrication. It returns to the reservoir through the case drain return line. If a service is operated, the system pressure will fall, the spring will push the control piston to the right, increasing the swash plate angle and thus the piston stroke. Pump output will increase to maintain the pressure. When the service reaches its required position, output pressure will again rise, and the swash plate will return to its no-load position. On some pumps, a solenoid-operated depressurizing valve, offload valve, can be used to block delivery to the system and to offload the pump. System pressure is maintained and the pump output falls to below 1000 psi, allowing case drain oil to circulate, lubricating and cooling the pump. This valve is useful in the event of a leak in that part of the system supplied solely by its pump. The solenoid is energized to offload the pump, so in the event of solenoid failure, the pump will continue to operate. The case drain fluid can become very hot, so it, and in some cases the system return fluid, is often passed through a cooler before being returned to the reservoir. The cooler usually consists of a heat exchanger matrix in the fuel tank, thus helping to warm the cold fuel as well as cooling the hydraulic fluid. Engine-driven hydraulic pumps cannot normally be disconnected from the engine, so in the event of an engine fire or an internal pump leak, it is necessary to have a method of isolating the pump from the flammable hydraulic fluid supply. This is achieved using a motorized firewall shutoff valve. The valve is open during all normal operations and only closed when it is called for in an emergency checklist. If the pump continues to rotate with this valve closed, it will rapidly suffer damage because of the lack of any cooling or lubricating fluid. To summarize, there are three types of pump in use: the simple hand pump and the two power-operated pump types. These are the constant delivery fixed volume type and the constant pressure variable volume type. These two pumps can be driven from a number of different sources, including the engine, an electric motor, an air motor, or a hydraulically operated motor from another system. Some aircraft have a ram air turbine-driven pump available for emergency operation. Remember that systems using a constant delivery fixed volume pump must also have both an automatic cutout valve and an accumulator in the system. In this lesson, we will now look in greater detail at some of the other components that make up an aircraft's hydraulic system. The first component we are going to discuss is the reservoir. You may think that in a sealed leak-free system, a reservoir would not be necessary. However, that is not true. Firstly, no system can ever be leak-free. In fact, we have already said that a very small amount of fluid is allowed to leak across the seals of actuators in order to lubricate them. Also, the fluid expands and contracts as it is heated and cooled. And as we shall see later, some types of hydraulic actuator need more fluid when they are extended than when contracted. The extra fluid is stored in the reservoir when not required. Most hydraulic systems also have accumulators fitted, and these will contain variable amounts of fluid depending on the system configuration. Again, we will discuss these in greater detail shortly. When a hydraulic pump is operating, as well as supplying pressure at its outlet, it also, of course, sucks fluid in at its inlet. This suction causes a big drop in the pressure of the fluid and can lead to low temperature boiling and the formation of bubbles. When these bubbles pass through to the pressure side of the pump, they then implode with great force. This is known as cavitation, and if allowed to happen, it can cause severe damage to the pump. The sound of pumps operating while cavitating can range from a low-pitched steady knocking sound, like on a door, to a high-pitched and random crackling, similar to a metallic impact. The reservoir helps to prevent cavitation by providing a head of fluid for the pump. To do this, the reservoir is located higher in the system than the pump to produce a positive pressure at the pump inlet. In many installations, the reservoir is also pressurized with air from the engine compressor to further increase the fluid pressure at the pump inlet, thus reducing the possibility of cavitation at high altitude. Another way that reservoirs are pressurized is by the bootstrap method. A piston sits on top of the fluid in the reservoir. It is pushed down by an actuator powered from its own hydraulic system, pressurizing the fluid. When the system is not operating, the pressure is held by the non-return valve. The reservoir also contains connections for suction pipes to the pumps and return pipes from the system, a quantity transmitter unit to allow the flight crew to monitor the system for correct servicing and in-flight leaks, a filling inlet, normally sealed with the filler cap. Note the strainer in the filler inlet, preventing debris entering the reservoir, and, in some cases, a temperature sensing probe, which may be used to operate a fluid temperature gauge and/or an over-temperature warning light. The baffles and fins are fitted to prevent sloshing and foaming of the fluid during in-flight manoeuvring. In systems which are fitted with more than one pump, usually the main pump is engine-driven, whilst the backup may be electrically or pneumatically driven, or may even be a hand pump. The main pump will draw its fluid through a stack pipe in the reservoir, whilst the backup will collect its fluid from the bottom of the reservoir. This ensures that if fluid is lost from that part of the system supplying the main pump, or supplied solely by the main pump, a reserve of fluid for the backup pump will still be available. It is very important that hydraulic fluid is kept free of foreign bodies. Any debris would quickly damage the pump and components. It would also cause problems in things such as pressure relief valves, as they can have very narrow passages which are easily blocked by foreign particles. Filters are fitted in both suction and pressure lines, that is, on both sides of the pump. The suction filter protects the pump, and the pressure filter ensures the cleanliness of the hydraulic fluid during use. There is also sometimes a filter fitted in the fluid return line to the reservoir to remove particles picked up during component operation. Filters remove foreign particles from the fluid, thus protecting the seals and working surfaces of the components. Some filters are fitted with a device which senses the pressure differential across the filter element and releases a visual indicator in the form of a button or illuminates a warning lamp when the pressure differential increases as a result of the filter becoming clogged. False indication of element clogging as a result of high fluid viscosity at low temperature is prevented by a bimetal spring, which inhibits indicator button movement at low temperatures. Other filters are fitted with a relief or bypass valve, which allows unfiltered fluid to pass to the system when the element becomes clogged. In this type of filter, the element must be changed at regular intervals before clogging occurs. Some filters combine both systems, with the warning indicator set to operate shortly before the bypass valve opens. Individual components often have a small filter fitted to their inlet connection, and constant pressure pumps will have a case drain filter to help monitor pump condition. We will cover the term case drain when discussing pumps. Filter elements may be manufactured from paper, felt or gauze, from metal wire, or from a combination of these materials. All elements, except those made from wire, are usually discarded when removed, but wire elements may usually be cleaned. Cleaning by an ultrasonic process is normally recommended, but if a new or cleaned element is not available when the filter becomes due for check, the old wire element may be cleaned in a suitable solvent as a temporary measure. An accumulator is a device used to store hydraulic fluid under pressure. Two different types of accumulator are illustrated here, but many other types are used. However, the two shown are those most commonly in use in aircraft systems. Whatever its shape, the chamber of the accumulator is split into two parts by a separator. In the case of the cylinder, a floating piston is used, whilst the spherical accumulator has a flexible diaphragm. For the purpose of this explanation, we will concentrate on the cylindrical type, as this is the most common of all. The volume on one side of the floating piston is pressurized with air or nitrogen, and the other is connected to the hydraulic system pressure line. The gas side of an accumulator is normally inflated through a charging valve, which may be attached directly to the accumulator or installed on a remote ground servicing panel and connected to the accumulator by means of a pipeline. The charging valve usually takes the form of a non-return valve, which may be opened by means of a plunger in order to relieve excessive pressure. To pre-charge or check the gas pressure, the system hydraulic pressure should be released. This will allow the gas pressure to move the floating piston to the bottom of the accumulator. When a pump is operating and hydraulic pressure builds up in the system, the gas is compressed until fluid and gas pressure equalize at normal system pressure. At this point, the pump commences to idle, and system pressure is maintained by the accumulator. The accumulator gas pressure gauge will now read system pressure. A non-return valve is fitted upstream of an accumulator in order to prevent fluid from the accumulator being discharged back through the pump to the reservoir. The accumulator carries out a number of functions in the system. It helps to dampen out pressure fluctuations. It allows for thermal expansion and contraction of fluid trapped in the pipes. It can provide a small emergency supply of fluid to the system in the event of pump failure. The initial gas charge of the accumulator is greater than the pressure required to operate any service, and the fluid volume is usually sufficiently large to operate any service once, except that brake accumulators normally permit a guaranteed number of brake applications, or the ability to stop the aircraft during a rejected takeoff. If the system is using a constant delivery fixed volume type pump with an automatic cutout valve, it will prolong the period between cut-out and cut-in of the automatic cutout valve, and so reduce the wear on the pump. Operation of the automatic cutout valve will be explained shortly. The accumulator will also provide the initial fluid when a selection is made and the pump is cut out, or at minimum stroke. If a service is selected, a supply of fluid under pressure is available until pressure drops sufficiently to bring the pump online. Incorrect pre-charge pressure of the main accumulator can cause the automatic cutout valve to cut in and out too frequently. This may cause rapid fluctuations of system pressure, which can be felt and heard as hammering in the system. This can rapidly cause damage to the system if it is not dealt with. An automatic cutout valve, ACOV, is fitted to a system employing a constant delivery fixed volume pump to control system pressure and to provide the pump with an idling circuit when no services have been selected. The ACOV consists of a piston, which is sensing system pressure. This is opposed by a spring. The piston is controlling a poppet valve. The ACOV operates in two modes. These are known as cut-in and cut-out. The valve is in the cut-in position when spring pressure is greater than pump output pressure. The piston is fully down and the poppet valve is closed. Cut-out is when hydraulic pressure is greater than spring pressure. The piston moves up and the poppet valve is open. This allows the pump output to return to the reservoir. With the system not operating and the pressure zero, the ACOV will be in the cut-in position. When the pump starts operating, pressure will build up until when normal system operating pressure is reached. The pressure on the bottom of the piston will overcome the spring. The piston will move up, opening the poppet valve and allowing the pump to return its fluid output to the reservoir without any load. There will still be fluid flowing through the pump to cool and lubricate it. This is the cut-out position. System pressure will be held on the bottom of the piston by the non-return valve. When a service is operated, system pressure will fall. The spring force will now be greater than the hydraulic pressure, so the piston will move down, closing the poppet valve. This will cut off the pump return to the reservoir and allow it to operate the service. The ACOV will remain in the cut-in position until the service reaches the end of its travel and pressure builds up again. It will then return to the cut-out position. This type of system needs a reservoir of fluid energy downstream of the automatic cutout valve. Otherwise, any slight leakage through components or from the system would result in frequent operation of the valve and frequent loading and unloading of the pump. An accumulator fulfills this, as well as a number of other functions. The time between cut-out, offload, and cut-in, onload of the ACOV is a good indication of the condition of the system. External leakage will cause a reduction in the operating period, with frequent loading and unloading of the pump. Internal leakage, usually caused by a piston seal failure, will similarly cause frequent loading and unloading of the pump. This could also cause an increase in fluid temperature due to the extra work being done by the pump. That is the end of the lesson on components. To summarize the main points, a reservoir provides both storage space for the system fluid and sufficient airspace to allow for any variations of fluid volume in the system, which may be caused by actuator ram displacement or by thermal expansion. It compensates for small leaks, and it provides a head of fluid for the pump. Most reservoirs are pressurized to provide a positive fluid pressure at the pump inlet in order to help prevent cavitation. Filters are used to protect pumps and other system components from damage caused by foreign particles in the fluid. An automatic cutout valve is fitted to a system employing a constant delivery fixed volume pump to control system pressure and to provide the pump with an idling circuit when no services have been selected. Finally, an accumulator is fitted to store hydraulic fluid under pressure in order to dampen pressure fluctuations, to allow for thermal expansion, to provide an emergency supply of fluid to the system in the event of pump failure, and to prolong the period between cut-out and cut-in time of the ACOV, and so reduce the wear on the pump. It also provides the initial fluid when a selection is made and the pump is cut out. In this lesson, we will examine the components that are used to convert hydraulic pressure into mechanical movement. Hydraulic actuators, or jacks, are used to convert fluid flow into linear or rotary motion. They vary in size and construction depending on the operating loads, but all consist of an outer cylinder within which slides a piston and seal assembly. Attached to the piston is a piston rod, or ram, which passes through a seal and wiper ring assembly fitted into the end of the cylinder. Three types of actuator are used for different purposes in an aircraft system. They are single-acting, double-acting unbalanced, and double-acting balanced. A single-acting actuator is one that is hydraulically operated in one direction only. The force to move it in the other direction is provided by a spring. This type of actuator is normally used as a locking device, the lock being engaged by spring pressure and released by hydraulic pressure. A typical application would be a landing gear-up lock. This type of actuator has more fluid in the cylinder when the ram is extended than when it is retracted. The surplus fluid is stored in the reservoir when it is not being used. Double-acting unbalanced actuators are the type most commonly found in aircraft systems. These are operated hydraulically in both directions. Because of the presence of the piston rod, the piston face to which the rod is attached has a smaller area on which the fluid can act than the other face. As we know, force is equal to pressure multiplied by area. So more force can be applied during extension of the piston rod than during retraction. If equal pressure is supplied to both sides of an actuator of this type, because of the difference between the areas on the two sides of the piston, the ram will extend. Normally, the operation which offers the greater resistance is carried out in the direction in which the piston rod extends. For example, in the case of landing gear, the rod will extend to raise the gear and retract to lower it. A double-acting balanced actuator is one in which equal force can be applied to both sides of the piston. This is achieved by having rods attached to both faces of the piston. It is often used in applications such as nose wheel steering and hydraulically powered flying control systems. Either one or both ends of the piston rod may be connected to a mechanism, or in many instances, the rod is connected to the airframe and the body moves to operate the service. When fluid is trapped between the piston of the actuator and a non-return valve, or a selector valve at its neutral position, a hydraulic lock is said to be formed. Because the fluid is incompressible and is unable to flow through the system, the piston cannot move, even if an external load is applied to it, and is therefore locked in its position. In our example, the gear lever has been selected to off. The weight of the gear is now being held by a hydraulic lock. Hydraulic motors are a form of rotary actuator, and are sometimes connected through gearing to operate screw jacks on such components as trailing edge flap drives. Illustrated here is the B747 trailing edge flap drive motor. It is mounted directly onto a gearbox, which in turn transmits the drive to the flaps through a torque tube. Hydraulic motors can also be used to drive generators or pumps. In some aircraft, they are used for driving a hydraulic pump unit, thus enabling power to be transferred from one hydraulic system to another, without transferring fluid. In the setup shown here, the hydraulic motor is driven from the yellow system, and the pump is pressurizing the green system. So this particular power transfer unit, PTU, would operate in the event of a main pump failure in the green system. Note that there is no exchange of fluid, so the two systems remain separate. The construction of a hydraulic motor is generally similar to the construction of a multi-piston pump, with the pressure which is being fed into the pistons being used to rotate them around the swash plate. However, the swash plate angle is usually fixed. Therefore, the speed of a hydraulic motor is usually dependent on the flow rate of oil into it. A hydraulic motor will often have a flow control valve in the supply line to it. The purpose of this valve is to maintain a constant flow of fluid to a particular component, allowing it to operate at a constant speed, such as would be required in a trailing edge flap system. A simplified flow control valve is shown here. It has a piston with a number of holes in it, through which fluid can freely flow. The piston controls the position of a variable orifice valve. Inlet pressure is felt on one side of the piston, with a spring pushing on the other. If the inlet pressure increases, then the flow rate through the valve will tend to increase. However, the increased pressure will be felt on the piston, which will move the valve towards closed, thus reducing the flow rate. The opposite will happen if the pressure reduces. The spring will push the piston to the right, the valve will open, allowing an increased flow. Thus, for variations in inlet pressure, the flow rate through the valve will remain constant. To summarize then, hydraulic actuators can be single-acting, double-acting balanced, or double-acting unbalanced. Irrespective of what type of actuator it is, if fluid is trapped between the actuator piston and a valve, the actuator will be hydraulically locked and unable to move. A hydraulic motor is generally similar in construction to a multi-piston pump. However, the swash plate angle is usually fixed. Consequently, the speed of a hydraulic motor is usually dependent on the flow rate of oil into it. In this lesson, you will learn about the components used to control, limit and maintain the pressure in an aircraft's hydraulic system. The normal operating pressure of the hydraulic system in a large modern aircraft is 3,000 pounds per square inch, psi. Smaller aircraft may have systems operating at 1,500 psi. Maximum system pressure is set and adjusted by the spring in the control piston, for a constant pressure variable volume pump. Whilst in a system using a constant delivery fixed volume pump, this function is carried out by the automatic cutout valve, or ACOV. A number of other components are used to maintain or limit fluid pressure in various parts of a hydraulic system. Relief valves are used to relieve excess pressure caused by thermal expansion, thermal relief, or by failure of the normal system pressure control device, full flow relief. In the flap system, they are used for mechanical overload protection, flap relief. All act in a similar manner, relieving the excess pressure by returning fluid back to the reservoir. Thermal relief valves are usually fitted in lines isolated by non-return valves or selectors. The fluid trapped in these lines will attempt to expand if the temperature increases. This will cause an increase in pressure. If the pressure rises to approximately 10% higher than normal system pressure, then it will overcome the spring, pushing the ball off its seat. This will open a small orifice, allowing a small amount of fluid to flow back to return, thus relieving the pressure, allowing the valve to close again. In some systems, a full flow relief valve or high pressure relief valve is fitted downstream of the pump to bypass full pump output to the reservoir in the event of failure of the normal pump control system. A pressure maintaining valve or priority valve isolates secondary services from the pressure supply if system pressure falls below a predetermined value, thus giving priority to the operation of the primary services. Prior to system startup, with no pressure in the system, the spring will hold the pressure maintaining valve on its seat, cutting off the fluid supply to the secondary services. When normal operating pressure is available, the pressure acting on the bottom of the valve will be sufficient to push it up against the spring, allowing fluid to flow to the secondary services. The valve will now monitor system pressure. If pressure should fall, either because of high demand or a system fault, the spring will overcome the hydraulic pressure on the bottom of the valve, pushing it down, closing off the supply to the secondary services, giving priority to the primary services, until the pressure returns to normal. In aircraft with a single hydraulic system, a subsystem for the operation of the powered primary flying controls is often fed through a pressure-maintaining valve, with the flying controls having priority over other services. The subsystem may also have a separate accumulator and a backup pump, such as a ram air turbine. Most modern aircraft will have multiple hydraulic supplies available for flight controls. 2, 3, or even 4 independent hydraulic systems can simultaneously supply power for the primary flying controls. On the Boeing 747, for instance, each primary flying control is split into 2 separate parts, and each part is fed by 2 hydraulic systems, so a pressure-maintaining valve is not required. A pressure-reducing valve is often used to reduce main system pressure to a value suitable for operation of a service such as the wheel brakes. Prior to system startup, the spring will hold the valve fully down, opening fully both the high-pressure inlet port and the reduced pressure outlet. As system pressure rises, it will be felt on the valve base, pushing it upwards against the spring until the correct reduced pressure is reached. At this point, the inlet port will be fully closed. The valve will now modulate about this position to maintain the correct reduced pressure. If, because of back pressure, the reduced pressure should become excessive, then the valve will be pushed further upwards, opening the return port bleeding off the excess pressure. A brake control valve, or metering valve, is essentially a variable pressure reducing valve, which controls pressure in the brake system according to the position of the pilot's brake pedals or auto brake selections as required. When the pilot is not pushing on the brake pedal, system pressure on the bottom of the valve will push it up against the spring, closing off the fluid supply to the brakes. When the pilot applies the brakes, he pushes down on the spring, increasing its force, pushing down the piston and allowing fluid to flow to the brakes. The pressure in the brake line will be proportional to the force applied by the pilot. In this lesson, you have learned that the normal hydraulic system operating pressure for a large airliner is 3000 psi, while the systems on smaller aircraft may operate at 1500 psi. We have restated that in a system using a constant delivery fixed volume pump, the pressure is controlled by the automatic cutout valve, and that in a constant pressure variable volume system, the pressure is controlled by the pump itself. You should know that thermal relief valves allow for the thermal expansion of trapped fluid. You have seen that a high-pressure relief valve is often fitted to limit system pressure should the normal control system fail. You have also seen that a pressure-maintaining valve, or priority valve, isolates secondary services from the pressure supply if system pressure falls below a predetermined value, thus giving priority to the operation of the primary services. And that a pressure-reducing valve is often used to reduce main system pressure to a value suitable for operation of a service that requires a lower pressure. In this lesson, we will describe the devices that are used to control the flow of fluid to the various hydraulically operated services. The most common device used to control the flow of fluid is the non-return valve. This valve permits full flow in one direction, but blocks flow in the opposite direction, in a similar way to a diode in electrical circuits. This valve is also known as a check valve or non-reversible valve. In its simplest form, as shown here, the valve consists of a ball held in place by a lightly loaded spring. Fluid flowing in the direction of the arrow has no difficulty in overcoming the spring pressure and pushing the ball off its seat. However, if the fluid attempts to flow in the opposite direction, then it will force the ball onto its seat and form a seal. A restrictor valve, or choke, is designed to permit limited fluid flow in one direction and full flow in the other. As with the non-return valve, it is marked to assist with correct fitment. A solid arrow shows the direction of full flow, with a dotted arrow indicating restricted flow. When fluid is flowing in the direction of the restriction, the spring, assisted by fluid pressure, will push the valve onto its seat, closing the holes around its circumference, allowing fluid to flow only through the central orifice. When flowing in the opposite direction, fluid pressure will push the valve off its seat, allowing the fluid to flow through all holes. A restrictor valve is used to slow the operation of a service when either gravity, in the case for instance of gear lowering, or airflow in the case of flaps retracting, may cause that service to overspeed. The valve is always placed to restrict the flow of return fluid. If it was placed on the inlet side of the actuator, whose speed is being controlled, it would cause a pressure drop in the cylinder, leading to cavitation. This could cause damage to the actuator. You can operate the switch with your mouse to observe the operation of the restrictor valve as the gear moves up and down. The purpose of a selector valve is to direct fluid to the appropriate side of an actuator, and to provide a return path for fluid displaced from the opposite side of that actuator. Here, we show a simple slide-operated selector being used to operate the landing gear. In our example, the selector valve is mechanically connected to the gear lever. However, it is sometimes convenient to locate a selector valve at a position remote from the crew compartment. To eliminate the need for extensive mechanical linkages, the selector may be operated electrically, either by an electric motor or a solenoid. Shuttle valves are often used in landing gear and brake systems to enable an alternate hydraulic system to operate the same actuators as the normal system. During normal operation, free flow is provided from the normal system to the service, and the alternate line is blocked. If normal system pressure is lost and the alternate system is selected, alternate system pressure will move the shuttle valve across, blocking the normal line and allowing the alternate supply to operate the service. On many aircraft, the retractable landing gear is behind flush-fitting doors when it is retracted. For aerodynamic reasons, some of these doors are also closed when the gear is extended. It is important that the correct sequence of door opening and closing happens when the gear is raised or lowered. Sequence valves are fitted in the landing gear hydraulic circuit to ensure this. There are two types of valve in common use: mechanically operated and hydraulically operated. The mechanical type of valve consists of a piston in a cylinder connected to a plunger, with a spring pushing the piston in the closed direction. If this valve is being used in a gear down sequence, then the fluid will first be ported to the door. Fluid to the gear will be blocked by the piston. When the door is fully open, a striker connected to the door will push the plunger across, allowing fluid to flow to the gear actuator. A hydraulically operated sequence valve uses the change in hydraulic pressure as a service operates for its operation. In the diagram, hydraulic pressure in the supply line to the service being monitored is being felt on the bottom of the plunger. While the service is operating, this pressure will be low, allowing its spring to keep the plunger down. Fluid for the next service in the sequence is fed into the top of the valve, with its outlet port on the right. The spring, combined with the fluid pressure, will push the valve onto its seat, sealing the orifice. Once the first service reaches the end of its travel, pressure will now build up below the plunger. The plunger will move up, pushing the ball valve off its seat and allowing fluid to flow through to the next service. Modern jet aircraft are dependent on their hydraulic systems, not only for raising and lowering the landing gear, but for flight controls and many other services. For this reason, most aircraft use more than one hydraulic system, and in these systems, provision is made to fuse or block lines, particularly those in vulnerable areas, if a serious leak should occur. The devices used to do this are known as hydraulic fuses. Wheel brakes are normally protected by fuse units. Each individual brake unit will have a fuse. They are often co-located with the anti-skid modules in a safe area at the top of the wheel well. A modulator is used in conjunction with the anti-skid unit in a brake system. It allows full flow to the brake units on initial brake application, and thereafter a restricted flow as controlled by the anti-skid unit. Anti-skid protection is discussed in detail in the wheel brakes lesson. That is the end of the lesson. Here is a recap of the components that we have covered. The non-return valve permits full flow in one direction, but blocks flow in the opposite direction, in a similar way to a diode in electrical circuits. This valve is also known as a check valve or non-reversible valve. A restrictor valve or choke is designed to permit limited fluid flow in one direction and full flow in the other direction. A selector valve is used to direct fluid to the appropriate side of an actuator or motor and to provide a return path for fluid displaced from the opposite side. A shuttle valve allows an alternate hydraulic system to operate a service. Sequence valves are fitted in the landing gear hydraulic circuit to ensure that the gear and doors open and close in the correct sequence. Hydraulic fuses block lines in vulnerable areas if a serious fluid leak should occur. And finally, a modulator is used in conjunction with the anti-skid unit in a brake system. It allows full flow to the brake units on initial brake application, and thereafter a restricted flow as controlled by the anti-skid unit. In this lesson, we will look at the controls and indicators for the hydraulic system. Firstly, those used on older aircraft, and then we will examine the indications given to pilots on the electronic screens used on most new generation aircraft. Large aircraft with multiple hydraulic systems need fairly sophisticated control and indicating systems. Shown here is a typical hydraulic control and indicating panel from the flight engineer's station of an older large airliner with 4 separate hydraulic systems, labelled A, B, C and D. A clear window may be fitted in the reservoir to provide a means of checking fluid level during servicing. The reservoir may also be fitted with a float-type contents unit, which electrically signals fluid quantity to an instrument on the hydraulics panel in the crew compartment. The reservoir low quantity light will illuminate if the fluid quantity falls below a predetermined level. Fluid temperature is monitored by a temperature sensing element. If the temperature of the fluid in the reservoir becomes excessive, the high temperature light will illuminate. The firewall shutoff valve is used to shut off fluid at the pump inlet. Pulling the engine fire switch will close this valve. The flow bar is lit when the valve is open. Operation of the pump shutoff switch energizes the solenoid-operated depressurizing valve, offloading the pump. You will recall that operation of this valve blocks off delivery to the system, but allows pump cooling and lubrication fluid to continue to flow. There are air turbine motor-driven backup pumps in the B and C systems. The switches highlighted here control these pumps. The engine-driven pump case drain return fluid temperature is monitored in order to check pump condition. The lights highlighted here illuminate if the temperature becomes excessive. If the engine-driven pump outlet pressure is low, then a pressure-operated switch will illuminate the pump low pressure light. Systems B and C have electric motor-driven hydraulic pumps, which are used to power the brakes when the aircraft is being towed. They are controlled by the switches shown here. There are two power transfer units. They use hydraulic motors in systems B and C to drive pumps in systems A and D respectively. They are controlled by the switches highlighted here. The ram air turbine is deployed when the switch highlighted here is pressed. It will power hydraulic system B, which is used purely for the primary flying controls and wheel brakes. The system has two brake accumulators. If the accumulator pressure is low, the lights highlighted here will illuminate. Large aircraft have electrically operated pressure gauges fitted on the hydraulics panel to indicate system pressure. Smaller aircraft may have a direct reading pressure gauge in the cockpit. In order to protect the system from leaks in the pipework to the gauge, and to prevent the cockpit from being filled with hydraulic fluid in the case of a leak, a pressure relay is often fitted in the line. The pressure relay consists of a cylinder with a free-floating piston inside it. System pressure is fed into one side of the piston, with the other side being connected through a pipe filled with fluid to the gauge. System pressure is transmitted through the piston to the fluid supplying the gauge. In the case of a leak in the pipework to the gauge, or in the gauge itself, only the fluid between the pressure relay and the gauge will be lost. Direct reading gauges are often fitted to accumulators and reservoirs to enable servicing operations to be carried out. Warning of overheating of electrical motors, which are used to drive backup emergency hydraulic pumps, may be provided by fitting a temperature sensing element in the casing. In the event of a motor overheat, the warning light will illuminate. In more modern aircraft, hydraulic system information can be viewed on electronic screens. The system is normally configured so that in the event of a failure, a warning will be enunciated, and the relevant page will be automatically displayed. This diagram shows an electronic screen from an Airbus aircraft, displaying the hydraulic system configuration and indications. There are three independent systems. They are identified as the green, blue, and yellow systems. Reservoir quantities are graphically displayed here. The indication is green unless the reservoir level is low, when it changes to amber. These boxes indicate pump status. They show in line for a pump which is operating, and cross line for a pump which is not. System pressure is displayed at the top of each system. The ram air turbine and the power transfer unit configurations are also displayed. The flow arrowheads are empty when they are not operating, and filled green when they are. Here is a typical hydraulic control panel from a modern four-engined aircraft. As you can see, it is much simpler than an older aircraft. However, again, there are four separate systems. The push buttons control the engine-driven pump depressurizing valves. They have pump low pressure lights integrated in them. The rotary switches control the electrically or pneumatically powered backup pumps, with their respective low pressure lights above. You will notice that the number 4 system switch has an extra position marked AUX. This position is used to operate a low-volume electrically powered pump to pressurize the brakes prior to engine start or when the aircraft is being towed. Each system has a master fault light. The cause of the fault can be found by checking system status on the electronic screen. You should now be familiar with the control and indicating systems used on old and new generation airliners. Here is a complete hydraulic system, showing many of the components we have discussed. To review any component, you may click on it. In this lesson, we will examine the high-pressure pneumatic systems that are used instead of hydraulic systems on some aircraft types. These systems are not generally used on modern transport aircraft, as large components such as landing gear are operated more efficiently by hydraulic power. However, these systems are still in use on some older aircraft, such as the Fokker F-27. Compressed air has some advantages over hydraulic systems. Air is universally available and it is free. The system is lighter because the air can be dumped overboard after use, so no return lines are required, and air is lighter than hydraulic fluid. There is no fire hazard, nor is air toxic. There are no viscosity problems with changes of temperature. The major disadvantage of air is that air is extremely compressible. The diagram shown depicts the high-pressure closed-center system used on the Fokker F-27. The two 4-stage compressors are driven from the accessory gearboxes of the turboprop engines. The unloading valve ensures that the system pressure is maintained at 3,300 psi by dumping excess air overboard. A shuttle valve enables the system to be charged or operated from an external source. Two components provide protection against the possibility of water freezing in the system: a moisture separator, which removes 98% of the water present in the air, and a dryer, which removes the remaining water using a desiccant such as silica gel or anhydrous aluminium silicate. There are a number of non-return valves in the system to prevent reverse flow of the air. Filters ensure that the air is clean before it enters the system. Three air bottles, which serve as both reservoirs and accumulators, are provided to store the high-pressure air ready for instant use. The main system has a large capacity bottle. There are two smaller bottles, one for the brakes and one reserved for emergency gear lowering. Most of the components operate with a pressure of 1000 psi, so the air is passed through a reducing valve before being used by the various services. There is a manually operated isolation valve which can be closed to facilitate system servicing. That is the end of the high-pressure pneumatic system lesson. You should now know the advantages and the major disadvantage of such a system.
In this series of lessons on landing gear, you will learn about the design and construction of both fixed and retractable landing gear, including retraction systems using hydraulic power. Steering will be discussed, and landing gear indicating systems will be explained, as well as the emergency lowering and safety systems that are available on most modern aircraft. In this first lesson, we will discuss the functions of the landing gear and then describe the various types of fixed gear. A detailed explanation will also be given of the operation of the oleo pneumatic strut. The
The functions of the landing gear are to provide a means of maneuvering the aircraft on the ground, to support the aircraft at a convenient height to give clearance for engines, propellers and flaps, and to facilitate loading and to absorb the kinetic energy of landing and provide a means of controlling deceleration through the brakes. Once airborne, the landing gear serves no useful purpose and is effectively dead weight. A vast amount of research has gone into the design of landing gear units in order to reduce their weight and the space they occupy when retracted. There are two types of landing gear layout. They are the tricycle layout, where there is a nose wheel unit forward of two main gear units, and the tail wheel or tail dragger type, with a tail wheel behind the main wheels. The tricycle gear has a number of advantages over the tail wheel type. There is no danger of tipping over onto its nose whilst taxiing in a strong tailwind. And there is a greatly improved forward view on the ground for the pilot. And lastly, it produces a much more level platform for loading. For these reasons, most aircraft now use the tricycle layout, with the two main gear units being positioned just aft of the center of gravity, supporting up to 90% of the aircraft's weight and absorbing all of the initial landing shocks. The nosewheel unit keeps the aircraft level, and in most cases also provides a means of steering. With slow, light aircraft and some larger aircraft for which simplicity is of a prime importance, a fixed, non-retractable landing gear is often fitted. However, the reduced performance caused by the drag of the landing gear during flight is offset by its simplicity, its reduced maintenance, and also its low initial cost. With higher performance aircraft, reducing the effects of drag is more important, and the landing gear is retracted into the wings or fuselage during flight. There are, however, penalties of increased weight, greater complication, and additional maintenance. There are three types of fixed landing gear shock absorption systems in common use. Those which have a spring steel leg, those which employ rubber cord, and those that have an oleo-pneumatic strut to absorb shocks. Spring steel legs are usually employed at the main landing gear positions. The leg consists of a tube or strip of tapered spring steel, the upper end being attached by bolts to the fuselage, and the lower end terminating in an axle, on which the wheel and brake are assembled. When rubber cord is used as a shock absorber, the landing gear is usually in the form of tubular struts, designed and installed so that the landing force is directed against a number of turns of rubber in the form of a loop. Some fixed main landing gears, and most fixed nose landing gears, as well as almost all retractable landing gears, are fitted with an oleo-pneumatic shock absorber strut. The design of individual struts varies considerably. However, the operating principle is the same for all. A simple oleo-pneumatic strut consists of two concentric cylinders, one free to slide inside the other. The cylinders are filled with hydraulic fluid and gas. The fluid and gas are kept apart by a separator piston. In this example, the outer cylinder is fixed rigidly to the airframe structure. It houses the lower inner cylinder and piston assembly. The wheels and axle are connected to the bottom of the inner cylinder. The inner cylinder is free to rotate and move up and down within the outer cylinder. However, rotary movement is prevented and up and down movement is limited by the torque links, which connect the inner and outer cylinders together. These links are sometimes also known as torsion or scissor links. The main gear is subject to torsion loads during ground maneuvering, and these loads are taken by the torque links. The smaller the radius of the turn, the greater will be the load felt by the torque links. So all turns should be made as wide as operationally possible. The area above the separator piston is filled with hydraulic fluid, and the area below is inflated with compressed gas, which may either be of air or nitrogen. The separator piston is a free-floating piston, which keeps the fluid and gas apart. The gas supports the weight of the aircraft on the ground, cushions bumps during taxiing, and absorbs the shock on landing. The purpose of the fluid is only to dampen oscillations and control the rate of compression and extension of the cylinders. The piston connected to the lower cylinder has holes in it which restricts the flow of fluid through the piston, thus dampening the movement between the cylinders. There is a component known as a flutter valve, which is fitted to the lower cylinder piston assembly. The flutter valve consists of a free-floating circular plate with a large central hole. It is free to move up and down within its housing. In the top of the inner cylinder, there is a small central orifice, plus a series of holes around the perimeter. If fluid is flowing upwards, the plate will be pushed up with it, blocking off the outer holes and allowing a limited flow only through the central orifice. However, if fluid is flowing downwards, then the plate will be pushed down, allowing a greater flow of fluid through all of the holes. The flutter valve will therefore limit the rate of movement more when the strut is extending than when it is contracting. With the aircraft stationary on the ground, the gas pressure will support the weight of the aircraft, with the lower cylinder approximately midway up its stroke. Bumps during taxiing are cushioned by the gas pressure and dampened by the limited flow of fluid through the orifice. After takeoff, the gas pressure will cause the lower part of the leg to extend to its fullest extent. On landing, however, the strut shortens and fluid is forced through the flutter valve. This restriction limits the speed at which the strut compresses. As the internal volume of the cylinders decreases, the gas pressure rises until it balances the downward force of the landing aeroplane. As the downward force of the landing decreases, the gas pressure acts as a spring and extends the strut. The flutter valve plate will move up with the fluid flow, blocking off the outer holes and further reducing the speed of upward movement of the outer cylinder, thus helping to prevent a bounce on landing. Evidence of a strut gas leak will be given by the strut not extending as far as it should with the aeroplane standing on the ground. In the case of the main gear, uneven amounts of shiny metal, which forms the hard outer coating of the strut, will be shown on each gear leg, with less shiny metal being visible on the leg with a gas leak. There are a number of methods used for connecting the wheel or wheels to the undercarriage leg. The most common methods are fork, half fork, cantilever, dual wheel, and multi-wheel using a bogie or truck. The methods are fairly self-explanatory, and an example of each is shown here. That's the end of the lesson. You should now know the 3 different types of fixed landing gear in common use today. Remember that it is the gas in the oleo-pneumatic strut that supports the aircraft and absorbs the shocks. The purpose of the fluid is to dampen oscillations and control the rate of movement of the cylinders. The torque links prevent rotary movement between the two cylinders. Finally, remember the methods commonly used for connecting wheels to the landing gear legs. You can test yourself on this by dragging the names from the list onto the correct pictures using your mouse. In this lesson, we will look at the design and construction of retractable main landing gear. The majority of modern transport aircraft and an increasing number of light aircraft are fitted with a retractable landing gear for the simple purpose of improving aerodynamic performance by helping to reduce drag in flight. Operating power is normally provided by a hydraulic system, but pneumatic or, on some small airplanes, electrical systems are sometimes used. A retractable landing gear is provided with mechanical locks to ensure that each leg is locked securely in the up or down position. It will have a means to indicate to the crew the position of each leg, and a means by which the landing gear can be lowered in the event of the failure of the normal power system. In addition, a system is provided to prevent retraction with the aircraft on the ground, and warning devices are fitted to help guard against landing when the gear is retracted. For aerodynamic reasons, wheel wells, which is where the wheels are housed, are normally sealed by doors which close after the gear is up. For the same reason, some of the doors may also close after the gear is locked down. This picture here shows the closed main gear doors on a Boeing 747. The geometrical arrangement and physical location of landing gear units on aircraft is by no means standard. The type, size, and position are decided at the design stage, having already taken into account the many factors that must be considered. The main considerations are the size and weight of the aircraft, the role the aircraft will fulfill, whether it has a high or low wing, and any associated gear stowage problems. Most modern aircraft will have the main landing gear attached to the wing, with some of the larger types having both wing and body gear. The body gear itself may actually still be steerable. This helps to reduce the turning circle and reduces the effect of wheel sideways movement or tire scrubbing, which affects multiple wheel landing gear systems. A number of aircraft are designed to operate in the dual freight and passenger carrying roles, especially from airports with limited resources. This has resulted in high-wing monoplane type aircraft where the floor of the aircraft is as close as possible to the ground for ease of freight loading. However, with some wings being as high as 6 or more meters off the ground, it is impossible to build a landing gear of sufficient strength to reach this far. So these aircraft incorporate the main gear in the fuselage. The diagram here shows a typical large aircraft retractable wing gear. The leg is attached to the wing spars by a cylindrical beam or trunnion on which the leg is free to rotate laterally. The upper part of the leg forms the outer cylinder of the oleo-pneumatic strut. The strut in a cylinder is connected to the wheel bogie or truck beam. The truck beam is able to pivot about its central point in a controlled way, as you see here. This allows all main wheels to be on the ground with the fuselage in the takeoff or landing attitude. There is an axle connected to a pair of braked wheels at each end of the truck beam. The wing gear torque links prevent rotation between the shock strut inner and outer cylinders without affecting their reciprocating action during normal operation of the strut. The drag strut, as shown here, supports the leg in a fore and aft direction. The upper and lower side struts support the leg laterally. They fold out when the gear is lowered, and are then held in place by the jury strut, which also folds out during extension. The jury strut is pulled over center by the downlock actuator, geometrically locking the gear down. If the gear is lowered without hydraulic power, then the over-centering action will be performed by an internal spring in the downlock actuator. To review the purpose of any of the components we've just mentioned, click on the appropriate label. For aircraft with the landing gear built into the fuselage, the requirements are basically the same as those for wing-mounted landing gear, except that often the gear mechanism may not be long enough for a geometric lock to be available, so an alternative provision has to be made for locking the gear both up and down. Depending on wheel layout, each wheel may require its own shock absorber unit, and possibly even a steering motor. A landing gear unit has to withstand various loads during its life. These loads are transmitted to the mountings in the aircraft structure, so these too have to be very strong. A landing gear is also subject to compressive loads, particularly during landing, but also whenever the weight of the aircraft is on the ground. The oleo-pneumatic strut helps to cushion these loads. The gear is also subject to rearward bending loads during braking. These loads are taken by the drag strut. There are also side loads during crosswind landings, also during takeoffs and taxiing. These loads are taken by the side struts. The nose gear is subject to longitudinal loads during pushback and towing. Again, these loads are taken by the drag strut assembly. You should now be able to identify the various components of the main landing gear, as well as understand their purpose. You should know, for instance, that the torque links take the main landing gear torsion loads during ground maneuvering, and that some larger aircraft have a steerable body gear, and that lastly the gear is normally locked down by a geometric lock produced by the over-center movement of the jury strut.
In this lesson, we will examine the function of the components that make up the nose landing gear. We will look at the operation of the nose wheel steering system, and then we will go on to discuss the problem of nose wheel shimmy. The nose undercarriage is usually a lighter structure than the main unit, since it carries less weight and is usually subject only to direct compression loads. It does, however, carry the attachment for the towing equipment, and so must withstand the shear loads associated with towing operations. Nose gear design is complicated by several requirements. It will normally have a steering system fitted, or it will have the ability to caster. But it must be able to self-center prior to gear retraction. Castering is explained later in the lesson. The nose gear also needs to have a method of countering shimmy. The diagram shows a typical large transport aircraft nose gear. As with the main gear, it has a drag brace assembly to give fore and aft support, and side struts for lateral support. The torque links transmit the steering actuator movements to the axle. We will look at steering, but later in this lesson. Castering is the ability of the nose wheel to turn to either side in response to the results of differential braking, or thrust or aerodynamic forces on the rudder, and to return back to its central position when the forces are removed.
To enable an aircraft without a nose-wheel steering system to be maneuvered about the airfield, the nose-wheel must caster freely. Automatic self-centering of the nose-wheel is essential prior to landing gear retraction. If the nose gear is not in a central position, that is to say, with the wheels pointing in a fore and aft direction, prior to its retraction, the restricted space available for its stowage will not be sufficient, and severe damage may be caused to the aircraft structure as the hydraulic system forces the gear upwards. Centering is achieved by either a cam system, which centers the nose wheel as the oleo-pneumatic strut extends on takeoff, or by hydraulic power being applied to both the nose wheel steering actuators when the landing gear is selected up. The graphic here demonstrates how it may be done using a cam system. A method of steering is required to enable the pilot to maneuver the aircraft safely on the ground. Early methods involved the use of differential braking in conjunction with a castering nose or tail wheel. This method is used on modern aircraft in the event of nose-wheel steering system failure. Light aircraft use a simple steering system, where the nose wheel is mechanically linked to the rudder pedals. Most large commercial aircraft use hydraulically powered steering systems, allowing the engines to be set at the minimum thrust for taxiing, thereby saving fuel. This method of steering is more accurate. It also reduces tire and brake wear and noise pollution. A hydraulically powered system may include a cockpit steering wheel or tiller, a control valve, steering cylinders to hold the nose gear, and a mechanical feedback device to hold the nose wheel at the selected angle. Steering is controlled, depending on the type of aircraft, by either the steering wheel or tiller, or by the operation of the rudder pedals. On some aircraft, the rudder pedals have a limited steering capability, allowing the pilot to keep the aircraft straight during takeoff, whilst normal ground maneuvering is achieved using the steering tiller. In hydraulically controlled nose-wheel steering systems, the operating pressure is derived from the aircraft hydraulic system. In the system shown here, hydraulic pressure is supplied from the same line that lowers the landing gear, so steering is only available when the gear is selected down. In some aircraft, a limited emergency supply may be provided by a hydraulic accumulator. There are two steering actuators which steer the nose gear. The restrictors in the pipelines between the steering actuators provide dampening for the steering operation and help to prevent nose wheel shimmy. As we mentioned, shimmy will be explained later on. The steering wheel or tiller is mechanically linked to the steering control valve. A follow-up linkage from the nose undercarriage gradually resets the control valve as the nose wheel turns. When the tiller is turned, it moves the control valve away from its central position. This ports fluid to the steering actuators, causing the nose gear to turn. You will notice that the jacks change direction as they pass through the center point of the strut. This is achieved by fluid transfer ports machined into the actuator cases. When the nose wheel reaches the selected angle, the follow-up linkage will centralize the control valve, shutting off fluid to the actuators. There is a safety bypass valve fitted between the two sides of the steering actuators. It is normally held closed by hydraulic pressure. The purpose of the safety bypass valve is to allow the nose wheel to caster if there is a hydraulic failure. If the hydraulic system should fail, the spring will push open the valve, allowing fluid to flow freely between the actuators, thus allowing the nose wheel to caster.
Some systems allow a limited amount of manual steering in this circumstance via the follow-up linkage. Some systems have the facility bypass the steering system during towing operations. In the system shown here, there is a bypass lever, which, when operated, opens a steering bypass valve. When the lever is operated by a ground engineer at the nose gear location, it opens the valve, allowing fluid to flow freely between the steering actuators. A bypass pin with a flag attached is fitted to hold the lever in the valve open position. The tractor can now tow the aircraft and turn the nose wheel as necessary. It is important that the bypass pin is removed before you commence taxiing. It is normally held aloft by the dispatching ground engineer as he moves clear of the aircraft, confirming to the pilot that it has been removed. Large aircraft with multi-wheel main gears have a problem with the main gears sliding sideways in turns. This is known as scrubbing and can quickly damage tires. This is particularly a problem for body gear, as they are near the center of the turn. To help improve the turning circle and reduce tire scrubbing, some aircraft have steerable body gear, which operates automatically in the opposite direction to the nose gear when the nose gear steering is operated. To minimize tire scrubbing, it is recommended that the aircraft be maneuvered on the ground using the largest turning circle possible. Tight turns should be avoided if at all possible, and the aircraft should be moved in a straight line for a short distance before stopping, in order to remove the twisting stresses from the main gear tires and legs. Due to the flexibility of tire sidewalls, an unstable, rapid, sinusoidal oscillation or vibration, known as shimmy, can be induced into the nose undercarriage. Worn or broken torque links, wear in the wheel bearings, and uneven tire pressures can all increase the tendency to shimmy. Excessive shimmy, especially at high speeds, can set up vibrations throughout the aircraft and can be dangerous. The best ways to keep shimmy to a minimum are to maintain the nose gear correctly, replacing worn-out parts, and by maintaining correct tire pressures. However, many nose wheels are still prone to shimmy, and there are a number of methods used to try and reduce its effects. As previously mentioned, hydraulic damping, in the form of restrictors, can be provided across the steering jack pistons or piston. A hydraulic or spring shimmy damper can be attached between the upper and lower oleo-pneumatic strut cylinders. Many larger aircraft use double nose wheels to help reduce shimmy, while twin contact tires have been found to be effective in minimizing tail wheel shimmy. That is the end of the lesson. You should now know that an aircraft with a free castering nose wheel can be maneuvered on the ground using differential braking. You have seen that the nose wheel can be steered both by using a tiller or the rudder pedals. You should now understand the term shimmy, and that it can be minimized by good maintenance, by fitting restrictors in the hydraulic nose wheel steering system, and by fitting a shimmy damper, or by fitting twin nose wheels or twin contact wheels. In this lesson, we will look at the indicating systems used to keep the crew informed of the position of the landing gear. We will then look at a typical hydraulically operated landing gear extension and retraction sequence. Although the landing gear, when selected down, may be at least partially visible from the crew compartment, it is not usually possible to be certain, by looking at it, that each landing gear is securely locked down. An electrical indicating system is used to provide a positive indication to the crew of the operation of the locks and the position of the landing gear. The system usually consists of microswitches or proximity sensors monitoring the up and down locks. These make or break electrical circuits when the locks operate, causing indications to change on the landing gear position indicator on the instrument panel. Microswitches are simple, mechanically operated electrical switches, which are operated by a striker plate when the gear reaches the required position. Most modern aircraft now use proximity switches. These are electronic devices with no moving parts. Each proximity switch consists of two components, a sensor and a target. When the sensor and target are in close proximity, a switch will be made. The picture shows the proximity sensors on a gear-down geometric lock. When the jury struts move to the over-center position, the sensor and the target move into close proximity, and a gear locked down signal is sent. The sensors are usually duplicated for safety reasons. Microswitches and proximity sensors are fully explained in the electrical systems lessons. Mechanical indicators may also be provided to show that the landing gear is down and locked if the electrical indicating system fails. For the main gear, these are often just buttons, which pop up on the top of the wing when the gear is locked down. They can usually be viewed from the fuselage windows. The nose gear will often have some sort of periscopic viewer in the cockpit floor through which the downlock can be seen. Some aircraft don't have mechanical indicators. Instead, they have duplicated electrical downlock sensors. On most modern aircraft, the electrical landing gear indicating system operates in such a manner that a green light is displayed for each gear when it is locked down. A red light is displayed when the gear is not locked in the selected position, and no lights are visible when the gear is up and locked. Bulbs are usually duplicated to avoid the possibility of false indications as a result of filament failures. Many large aircraft also have main gear door lock indicators to indicate that the hydraulically operated doors are closed and locked. These lights may be red or amber. Landing gear retraction systems can be hydraulic, electrical, or pneumatic in their operation. Here we will explain the operation of a hydraulically operated system. Pneumatically and electrically operated systems function in a similar fashion. Most modern commercial aircraft have hydraulically powered landing gear systems. The hydraulic power is normally supplied by the engine-driven pumps. There will be a backup system available in case of pump or engine failure. On some light aircraft, a self-contained power pack is used. This houses a reservoir and selector valves for the landing gear and flap systems. An electrically driven pump may also be included, or the system may be powered by engine-driven pumps. The diagram here shows a typical hydraulically operated main gear in schematic form. It has a number of components that were described fully in the hydraulic systems lessons. The gear actuator and door actuator are double-acting unbalanced actuators. The gear downlock and uplock actuators are spring-applied and hydraulically released. The gear is locked down by a geometric lock mechanism. There are two sequence valves controlling the sequence of gear and door operation. The two hydraulic lines from the selector are known as the up line and the down line. The up line is pressurized when the gear is selected up, and the down line is used for return fluid. The roles are reversed when the gear is selected down. The door is hydraulically opened and closed. It is closed when the gear is locked up or down. It opens to allow the gear to raise or lower. We will now look at the sequence of gear and door operation and the associated lights indications that you can usually expect to see on a modern airliner. For simplicity, we have only shown one main gear. However, the other main gear and the nose gear operate in the same manner. The gear lever will be within easy reach of both pilots, and the gear indicator lights are usually adjacent to it. The lights indicate the status of each individual gear. For simplicity, we will only show the lights for one gear when looking at the gear sequence. With the gear lever in the down position and the gear locked down and the hydraulically operated doors closed, the green gear down light will be on and the door open light will be out. The gear red light is a disagreement light. It illuminates at any time the gear and the lever are in disagreement. So when the gear is selected up, the first thing that happens is that the gear red light illuminates. However, the gear is still locked down, so the green gear down light remains. The selector valve controlled by the gear lever will send pressure fluid to the door actuator. The door now begins to open and the door open light illuminates. When the door is fully open, its gear sequence valve will redirect the pressure fluid to the gear downlock actuator and the gear actuator. The pressure fluid passes through the one-way restrictor valve in the full flow direction. The downlock actuator will begin to retract, breaking the geometric lock. The gear is now unlocked, so its green gear down light will go out. The gear actuator can now raise the gear. When the gear is fully up, the uplock roller will engage with the uplock actuator, causing, with spring assistance, the actuator to rotate, locking the gear up. Once the gear is locked up, the red gear light will go out. The door sequence valve now directs the hydraulic fluid to the door actuator, and the door closes. Once it is fully closed, the amber door open light will go out. With the gear up and doors closed, there will be no lights on the indicator. Once the gear is up and locked, and the door is closed, the gear lever is placed to the off position, leaving the gear unpressurized for the period of the cruise, so extending the life of the landing gear components and preventing unwanted leakage of hydraulic fluid. The sequence when the gear is selected down is basically the up sequence in reverse. When the lever is selected down, the red gear light comes on to indicate a disagreement between the lever and the gear. At the same time, fluid is directed to the door actuator. The door will open and the door light will come on. When the door is fully open,
the gear sequence valve will redirect the hydraulic fluid to the gear up-lock actuator and the gear actuator. The up-lock mechanism will rotate, releasing the gear. The gear actuator will now lower the gear, assisted by the weight of the gear. To control the speed of lowering, the return fluid from the gear actuator passes through a one-way restrictor valve in the restricted flow direction. You may wonder why the restrictor is in the up line and not in the down line. When the gear is going down, pressure fluid is passing through the down line and the up line is used for return. If the restrictor was in the down pressure line, as shown on the left, the suction caused during lowering by the weight of the gear on the actuator piston pulling fluid through the restriction could be sufficient to cause cavitation of the fluid in the actuator and pipeline. Cavitation is not a good thing. It is fully explained in the hydraulic systems lessons. With the restrictor in the up or return line, as shown on the right, the speed of lowering is still controlled, but there is no problem with cavitation. Also, if the gear has to be lowered under its own weight, without hydraulic pressure available, the fluid, displaced from the actuator, will still pass through the restrictor, so the speed of lowering will still be controlled. When the gear approaches the fully down position, a powerful spring in the lockdown actuator will push the geometric lock over center, locking the gear down. The red gear light goes out, and the green light comes on. Once the gear is locked down, the door sequence valve directs fluid to the door actuator, and the door closes. The door light goes out. Newer aircraft with large LCD screens will normally still have independent landing gear position indicators, but they also have the ability to provide further information about the landing gear system on a screen, as in this Airbus A320 Electronic Centralized Aircraft Monitor, or ECAM presentation. When the gear is locked down, there are green, down-pointing triangles on both the undercarriage indicator and on the ECAM screen. When the gear is neither locked up nor down, the triangles on the ECAM screen are red and unlocked is displayed on the landing gear indicator. And when it is up and locked, the displays are blank. The door positions are depicted by the symbols highlighted here. They are green when the doors are locked, closed, and amber when they are not. To summarize gear indications, the most important indication is for gear down. This is almost invariably indicated by a green light or lights. Red lights are normally used to indicate that the gear is not locked in the selected position. And lights out usually indicates gear up and doors closed. You should now have an understanding of how undercarriage extension and retraction is accomplished hydraulically, including the purpose of the sequence and one-way restrictor valves. Since the correct operation of the landing gear is of the utmost importance, a number of safety features are included in the retraction and extension systems to ensure its correct operation under all conditions. Safety features are also built in to stop the gear being retracted when it's not safe to do so, and to warn the crew if they are attempting to land with the gear not extended. In this lesson, we will discuss these safety features. To avoid damage to the airframe structure, the nose wheel must always be aligned in the fore and aft direction prior to retraction. A number of methods are used to ensure that this happens automatically. One method already discussed is hydraulic nose wheel centering on aircraft with powered steering. Other systems use a self-centering cam, which will move the nose wheel into the correct position as the oleo-pneumatic strut extends on takeoff. To prevent inadvertent retraction of the landing gear when it's not safe to do so, a safety device is incorporated which prevents the landing gear selector lever being selected up. This safety device consists of a mechanical lock which retains the selector in the down position and is released by the operation of an electrically operated solenoid. On smaller aircraft, electrical power to the solenoid is controlled by switches mounted on the main gear shock absorber struts. When the struts are compressed, the switches are open. But as the struts extend after takeoff, the switch contacts close and the electrical supply to the solenoid is completed, thus releasing the selector lever lock and allowing the landing gear to be selected up. On larger aircraft, a number of additional criteria have to be met before it is safe to raise the gear. For instance, the main gear trucks may have to be tilted to the correct angle, and for the aircraft with body gear steering, the gear will have to be aligned fore and aft. Only then will the lever lock be released. A means of overriding the lock, such as a separate gated switch to complete the circuit, or a mechanical means of releasing the lock, is provided for use in the event of solenoid failure and for maintenance purposes. Flight crews should exercise great care in using this bypass facility. Normally, it should only be used when called for in a checklist, as raising the gear hydraulically, when parts of it are incorrectly positioned, can cause catastrophic damage to both the gear and the airframe. Landing gear ground locks, or locking pins, are further safety features which are intended to prevent inadvertent retraction of the gear when the aircraft is on the ground. They will usually consist of pins or metal sleeves which interfere with the operation of the gear in such a way that it is impossible for the gear to move when they are in position. They are fitted with warning flags which help prevent the crew from inadvertently getting airborne with them still in position on the gear. If they are still fitted when the crew do their external inspection, a further external check should be carried out after they've been removed, as getting airborne with them fitted will often require the dumping of fuel before landing again to have them removed. On some aircraft, after removal, they are stowed on board in a position visible to the crew. To guard against landing with the landing gear not locked down, an oral warning is incorporated in the system. An oral warning isolation switch is often provided to allow certain flight exercises to be carried out without unnecessary warnings. Different aircraft types use different criteria for the operation of the oral warning and isolation switch. These normally involve a combination of flap and throttle positions. In a typical system, if the flaps are at an intermediate position with the gear not locked down, and one or more of the throttles are retarded, the warning will sound. The isolation switch can be used to silence the warning. If, however, landing flap is selected with the gear not locked down, then again the warning will sound. But operation of the isolation switch will not silence it. If fitted, the Enhanced Ground Proximity Warning System, EGPWS, will give a too low gear warning, passing a specified radio altitude with the gear not locked down. EGPWS is covered fully in the series of lessons on aircraft instruments. A means of lowering the landing gear and locking it in the down position is provided to cater for the possibility of failure in the normal system. In most modern aircraft, the uplocks may be released electrically, as in the case of the Boeing 747, where the switches control electric motors which operate the uplocks, or mechanically, as in the case of the Boeing 737, where the handles in the cockpit are connected by cables to the uplock release mechanisms. In both of these cases, once the uplocks have been released, the landing gear lowers or free falls under its own weight, and the downlocks are engaged mechanically by springs. In the typical system depicted here, pulling the handle to the first detent releases the door uplock, allowing the door to fall open. Pulling the handle to the second detent releases the gear uplock, which allows the gear to drop to the down position. A heavy spring in the downlock actuator forces the over-center mechanism into the locked down position. If the gear has been lowered by this free-fall method, there will be no power available to close the hydraulically operated doors after extension, so they will remain open, and the door open light will remain illuminated. On some aircraft, the landing gear can be extended by an emergency pressure system, which may use alternative pipelines to the jacks. Pressure for the emergency system may be supplied by a hydraulic accumulator, a hand pump, an electrically powered pump, or even a pneumatic storage cylinder. That is the end of the lesson. You should now know how the landing gear can be lowered in the event of a hydraulic system failure. You should be familiar with the methods used for preventing the landing gear retraction on the ground and for preventing a landing being made with the gear up. Remember, however, that these systems are not foolproof. The pilot is ultimately responsible for ensuring that the aircraft is in the correct configuration for the phase of flight.
In this short lesson on aircraft wheels, you will learn about the components that make up a wheel and the materials from which a wheel is made. An explanation will also be given of the purpose and function of fusible plugs. The wheels and tyres of an aircraft support it when on the ground, and provide it with a means of mobility for takeoff, landing and taxiing. The pneumatic tyres help to cushion the aircraft from shocks due to irregularities in the ground surface, and take some of the shock on landing. The main wheels, and in a small number of cases the nose wheels, house brake units which control the movement of the aircraft on the ground, and provide a means of deceleration on landing. Because aircraft tyres are usually larger and stiffer than the tyres found on cars, wheels have to be specially designed to facilitate tyre replacement. There are two types of wheel in common use. They are the loose or detachable flange type and the divided wheel. Both the loose and detachable flange types of wheel are made with one flange integral with the wheel body and the other a separate removable part, which is machined to fit over the wheel rim. The difference between the loose and the detachable flange tyres is the method by which the removable flange is secured. In the loose flange type, the flange is retained by a locking device on the wheel rim and held in place by the tyre pressure. The detachable flange type of wheel has the flange secured to the wheel body by nuts and bolts. A detachable flange may be a single piece or 2 or 3 pieces bolted together. The advantage of the loose and the detachable flange type of wheel is that the tyre can be changed without removing the wheel from the aircraft. The type of wheel most usually found on aircraft is the divided wheel. It consists of 2 half wheels matched up and joined together by bolts which pass through the 2 halves. The bolts are fitted with stiff nuts, or if one half of the wheel is tapped, that is to say that the bolt hole has an internal thread cut in it, then each bolt is locked with a locking plate. In this particular example, the 2 halves are clamped together by bolts fitted with locking nuts and washers. The wheel shown here is designed to be used with a tubeless tyre. It has a seal incorporated at the joint to prevent abrasion between the 2 halves and provide an airtight fit. The inner and outer drive blocks are used to rotate the discs in the multi-disc brake units. These will be discussed in a later lesson. When in service, particularly during heavy braking, there is a tendency for the tyre to rotate or creep around the wheel. This creep, if excessive, will tear out the inflation valve on a wheel fitted with an inner tube, causing the tyre to burst. Creep is less likely to occur if the tyre gas pressure is correctly maintained. The procedures for doing this are explained in the aircraft tyres lesson, but additional features to prevent creep may be incorporated in the design of the wheel, and we'll look at 2 such features now. Wheels are often produced with a knurled flange. The inner face of the wheel flange is milled, so that the side pressure of the tyre locks the tyre walls to the flange. The wheel rim is tapered, so that the flange area is of greater diameter than at the centre of the rim. When the tyre is inflated, the side pressure forces the tyre outwards to grip the rim. Aircraft wheels are either cast or forged, then machined and ground to the required finish. They are made of either aluminium or magnesium alloy. Magnesium alloys are lighter. However, they are subject to corrosion if not correctly treated. And magnesium is flammable, so there is a greater risk of fire. For these reasons, aluminium alloys are normally used, unless low weight is essential. Whichever alloy is used, after initial machining has been carried out, an anti-corrosive treatment is applied, and a final finish using cellulose or epoxy resin paint is applied to each wheel. Wheels for tubeless tyres are similar in construction to those for tyres fitted with inner tubes, but are ground to a finer finish and impregnated with Bakelite to seal the material. Seals are used between the parts of the wheel to prevent leakage. Unlike wheels for tyres fitted with tubes, the valve is fitted into the wheel itself and is thus not affected by creep. Under extra hard braking conditions, the heat generated in the wheel, tyre and brake assembly can be sufficient to cause the pressure to rise to a level that the tyre cannot withstand, causing it to split, with possible catastrophic consequences for the aircraft. This is commonly known as a tyre blowout. To prevent a sudden blowout, fusible plugs or thermal plugs are fitted in some wheels with tubeless tyres. These plugs are screwed into holes in the wheel rim. They are sealed by a piston, which is held in position in the plug by a fusible alloy. Under excessive heat conditions, the alloy melts, allowing the piston to escape. This causes the tyre to deflate in a controlled manner. The important points to be taken from this lesson are related to the fusible plugs. Remember that they are fitted in the wheel rim, and they protect the tyres from explosion due to overheating by releasing the gas in a controlled manner if an excessive temperature is reached. In this, the first of 2 lessons on aircraft tyres, the construction of the 2 types of tyre fitted to aircraft, radial and cross-ply or bias, will be described. Aircraft wheels are fitted with pneumatic tyres, which may be tubeless or have an inner tube. Tyres fitted with inner tubes tend to be used on some light aircraft and on older aircraft. Most modern aircraft have tubeless tyres fitted. Tyres are usually inflated with nitrogen, which absorbs shocks and supports the weight of the aircraft, while the tyre cover maintains the shape of the tyre, transmits braking, and provides a wearing surface. If a tube is fitted, the tyre also restrains the tube and protects it from damage. The tyre is divided into regions or sections, as illustrated here. The tread of the tyre is situated in the crown and shoulder section. It is worth noting that the term tread is applied irrespective of whether the rubber is plain and smooth or moulded on a block pattern. The sidewall allows the tyre to be flexible, and the bead is seated inside the flange of the wheel. There are 2 types of tyre in common use. These are known as radial ply and bias or cross-ply tyres, the names originating from the way the tyres are constructed. The tyre consists of a casing made of plies of cotton, rayon, or nylon cords. The cords are not woven, but arranged parallel in single layers, and held together by a thin film of rubber, which prevents cords of adjacent plies from cutting one another as the tyre flexes in use. During construction of the tyre, the plies are fitted in pairs and set out so that the cords of adjacent plies are at 90 degrees to one another in the case of bias or cross-ply tyres, and from bead to bead at approximately 90 degrees to the centre line of the tyre in radial tyres. The tyre manufacturer gives each tyre a ply rating. This rating does not relate directly to the number of plies in the tyre, but is the index of the strength of the tyre. The ply rating is shown on the sidewall of the tyre. This tyre, for example, has a ply rating of 32, but it only has 18 plies. The tyre beads hold the tyre on its wheel. The beads are made of high tensile wire strands. Each wire strand is coated with rubber compound and is spiral wound into a coil of the specified diameter for the tyre. The plies are wrapped around the beads and turned up back onto themselves. If the tyre is designed to be used without an inner tube, a rubber lining is applied to its inner surface and the underside of the beads. This lining, which retains the gas pressure, forms a gas-tight seal on the wheel rim. The gas seal depends on a wedge fit between the underside of the tyre bead and the taper of the wheel rim. To absorb and distribute load shocks and protect the casing from concussion damage, some tyres have 2 narrow plies embedded in thick layers of rubber between the casing and the tread. These special plies are termed breaker strips. The most popular tread pattern is the ribbed type. It is formed from circumferential grooves around the tyre to assist in water dispersion, and to help prevent aquaplaning or hydroplaning. The grooves also help to improve contact grip between the tread and the runway surface. Nose wheel tyres, particularly those fitted to aircraft with the engines mounted on the rear fuselage, may have a chine or chines moulded onto the shoulder. These are rubber extensions, designed to direct water away from the engine intakes and so prevent flameouts due to water ingestion. A nose wheel tyre fitted to a single wheel installation will have a chine moulded onto both sides of the tyre, whilst on a double nose wheel installation, the chine is fitted only to the outer edge of each tyre. Whether the tyre is fitted with a tube or is tubeless, an inflation valve is required. In the case of the tyre with a tube, the valve forms part of the tube installation, whilst on a tubeless tyre, it is fitted directly onto the wheel rim with a rubber sealing gasket. Each inflation valve is fitted with a non-return valve. The valve core is not considered to be a perfect seal. Therefore, the inflation valve must always be fitted with the valve cap. The valve cap also prevents dirt from entering the valve. It is important when doing your external check of the aircraft that you check that the valve caps, which are normally coloured yellow, are fitted. They will slow down the loss of pressure in the event of a valve failure. The differences in landing speeds, loading, landing gear surfaces, and landing gear construction of aircraft make it necessary to provide a wide range of tyre sizes, types of tyre construction, and inflation pressures. In terms of inflation pressures, tyres are split into 4 main groups, identified as low, medium, high, and extra high pressure tyres. Low pressure tyres are designed to operate at a pressure of 25 to 35 pounds per square inch, psi, or 1.73 to 2.42 bar. These are fitted to aircraft using grass surfaces for takeoff and landing. Medium pressure tyres operate at a pressure of 35 to 70 psi, or 2.42 to 4.83 bar, and are used on grass surfaces or on medium firm surfaces without a consolidated base. High pressure tyres operate at a pressure of 70 to 90 psi, or 4.83 to 6.21 bar, and are suitable for concrete runways. Extra high pressure tyres are fitted to most large modern airliners. They operate at pressures of over 90 psi, with some tyres of this type being inflated to 350 psi or 24.2 bar. These tyres are suitable for concrete runways. Tyres in use must be kept inflated to the correct pressure, using nitrogen or another inert gas with less than 5% oxygen content, as underinflated tyres may move or creep around the wheel, and overinflated tyres will cause other types of failure. It is estimated that 90% of all tyre failures can be attributed to incorrect gas pressure. Overinflation will cause excessive wear to the crown of the tyres, whilst underinflation is the cause of excessive shoulder wear and creep. On some modern aircraft, real-time tyre pressures can be displayed on the flight deck, as shown here on this A320 electronic display screen. The manufacturer will set a maximum ground speed to which a tyre can be subjected. This will be marked on the side of the tyre. It is important that this speed is not exceeded, as damage, including possible tread separation, may occur. You should now have an understanding of how the two types of tyre are constructed. Bear in mind that the ply rating of a tyre is not necessarily an indication of the number of plies. It is an indication of the tyre's strength. You also need to be aware of the effects of both under and over inflation of tyres. In this lesson, we will discuss the problems of creep and of aquaplaning or hydroplaning. We will look at tyre wear and damage. We will examine the problem of tyre creep and see how it is monitored. To end the lesson, we will take a quick look at the process of retreading tyres. Aquaplaning or hydroplaning is a phenomenon caused by a wedge of water building up under the tread of the tyre and breaking its contact with the ground. Aquaplaning speed, measured in nautical miles per hour or knots, is the speed at which the tyre loses contact with the ground. It can be found by applying the formula aquaplaning speed equals 9 times the square root of p, where p is the tyre pressure in pounds per square inch, or aquaplaning speed equals 34 times the square root of p, where p is the tyre pressure in kilograms per square centimetre or bar. The possibility of aquaplaning increases as the depth of the tread is reduced. It is therefore important that the amount of tread remaining is accurately assessed. The coefficient of dynamic friction between the tyre and the ground will reduce to very low values, typically 0 when aquaplaning. Neither nose wheel steering nor braking will be effective when the wheels are aquaplaning. The heat generated between the tyre and the water, if the brakes are applied during aquaplaning, may be sufficient to melt the tread of the tyre. Here, you may try an aquaplaning calculation. Enter a tyre pressure between 50 and 300 psi. Calculate the aquaplaning speed and enter it in the box. Press Go to check your calculation. During your pre-flight inspection, tyres must be examined for cuts, bulges, embedded stones, metal or glass, signs of wear, creep and local sponginess. Cuts in the tyre penetrating to the cords render the tyre unserviceable. The cords will be recognisable as pieces of white fibrous material embedded in the rubber of the tyre. Whether the tyre can be repaired or must be renewed is governed by the depth of the cut. Bulges may indicate a partial failure of the casing. If the casing has failed, that is to say the fabric is fractured, then the tyre must be replaced. Any flat spots on the tyre tread, especially those caused by skidding or aquaplaning, must be examined with great care to determine if the fabric of the tyre has been weakened unduly. Foreign bodies, such as pieces of metal or glass or stones embedded in the tyre, must be removed, and the cuts probed with a blunt tool by a technician to ascertain their depth. Repair or renewal of the tyre is governed by the extent of the damage. If you are in any doubt about the serviceability of a tyre, have it checked before flight by a suitably qualified technician. The amount of wear that a tyre can be subject to varies with different tyre types. Some tyres have marker tie bars in the centre groove. On others, the centre groove, or the two grooves either side of centre, are used as wear indicators. Generally, pattern tread covers worn to the base of the marker grooves, or to the marker tie bars for 25% of the tyre circumference, or plain tread covers worn to the casing cords, must not be used. For special high-speed applications, some tyres have a layer of fabric woven into the tread. These tyres will have reinforced tread printed on the sidewall. This fabric may become visible during normal wear. This is perfectly normal, and the tyre can continue in service with this layer visible. With the increased size of modern airports, taxi distances have also increased, thus increasing the amount of tyre wear and risk of damage. To minimise tyre wear, it is recommended that a speed of no more than 25 miles or 40 kilometers per hour should be reached during the taxi run. When a tyre is first fitted to a wheel, it tends to move slightly around the rim. This phenomenon is called creep, and at this stage it is considered normal. After the tyre settles down, however, this movement should cease. In service, the tyre may tend to continue to creep around the wheel. If this creep is excessive on a tyre fitted with an inner tube, it will tear out the inflation valve and cause the tyre to burst. Creep is less of a problem with tubeless tyres, as long as the tyre bead is undamaged and any pressure drop is within limits. Creep is less likely to occur if the tyre gas pressure is correctly maintained. In order to detect creep, 2 white lines, known as creep marks, are painted, one on the wheel and a matching one on the tyre. If the lines become misaligned, then the tyre is suffering from creep. Provided the marks overlap each other, the tyre can remain in service. If, however, the marks become completely misaligned, then the tyre must be changed. Many aircraft tyres that become damaged in service can be successfully repaired. Tyres of which the treads are worn out, flat-spotted or otherwise damaged, but of which the core body or carcass is intact, can be retreaded. Retreading and repairing aircraft tyres has been a common practice for many years, and can save aircraft operators considerable sums of money. Tyres can be retreaded or repaired for continued service at a cost much lower than that of a new tyre. EASA regulations require retreading and/or repairing of aircraft tyres to be performed in certified retread and repair stations by or under the responsibility of qualified and certified technicians. You should now have a good understanding of how much tyre wear and damage is acceptable. The aquaplaning formula is quite important, but probably more important is the fact that if the tyre is aquaplaning, then its coefficient of friction is at or near 0. You should understand the problems associated with creep and how it can be monitored. Finally, remember that an aircraft tyre whose tread is worn beyond limits can normally be repaired or retreaded many times. In common with most braking systems, aircraft wheel brakes function by using friction between a fixed surface and a moving one to bring an aircraft to rest, converting kinetic energy into heat energy. The amount of heat generated in stopping a large modern aircraft is enormous. The problem of dissipating this heat has been a challenge to aircraft designers and scientists for many years. Braking systems have been improved, but aircraft have got faster and heavier, making heat dissipation a constant problem. The use of reverse pitch on propeller-driven aircraft and reverse thrust on jet-engined aircraft, plus the use of ground spoilers, has helped reduce the work the brakes need to do. But even with these, the need for powerful brakes still exists. In this, the first in a set of 3 lessons on wheel brakes, the components that make up a typical aircraft braking system will be described. All modern aircraft now use plate or disc brakes operated by hydraulic systems as their means of slowing down or stopping. Light aircraft use a very similar system to that used on cars. It consists of a pair of fixed friction pads bearing on or gripping a metal disc, which rotates with the wheel. The friction pads are made of an inorganic material, and the plates are of forged steel, with an especially case-hardened surface. With no pressure applied to the toe brake pedal, the pads are knocked away from the disc by the action of it rotating. If pressure is applied to the toe brake pedal, hydraulic pressure will build up in the slave cylinder behind the piston. This pressure will cause the piston to move over within the caliper unit, pushing the brake pad against the disc. The reaction of the right-hand brake pad pushing against the disc will cause the caliper unit to move in the opposite direction, carrying the left-hand pad with it until the disc is squeezed between the two pads. The force applied to the brake pads will be proportional to the effort applied to the toe brake pedal. The toe brake pedals can be applied together, or, if differential braking is required for ground manoeuvring, the toe brakes can be used separately. When brake pressure is released, imperfections in the rotating brake disc once again cause the brake pads to move apart, so that the residual braking effect is minimal. On a simple light aircraft system, the pilot is able to apply sufficient pressure to the pedal with his foot to operate the brakes and slow the aircraft down. However, on larger aircraft, the pressure required to operate the brakes is greater than can be generated by the pilot's feet. So aircraft hydraulic system pressure, controlled by metering valves connected to the foot pedals, is used. There will be a primary and an alternate hydraulic source available. The alternate source often has independent pipework. There may also be an accumulator for use in the case of total hydraulic system failure. On large aircraft, the braking surface is increased by using multiple brake plates, known as rotors, sandwiched between layers of friction material mounted on assemblies known as stators. This greatly increases the surface area, thus increasing the braking ability and helping to reduce the brake temperature. In this sort of construction, the rotating brake plates, or rotors, are key to revolve with the outer rim of the wheel, and the stationary pad assemblies, or stators, carrying the friction material, are key to remain stationary with the axle. The actuating pistons are housed in a fixed torque plate. They push on the sliding pressure plate. The stator and rotor assemblies are fitted between the pressure plate and a fixed thrust plate. When the brake is applied, hydraulic pressure pushes the actuating pistons, squeezing the rotors and stators between the pressure plate and the thrust plate. The harder the brake pedal is pressed, the greater will be the braking force applied to the pressure plate by the pistons. On aircraft with undercarriage bogies, the torque developed during braking will attempt to rotate the bogie about its pivot point. This is prevented by brake torque rods attached to the landing gear leg. Recent technological advancements in heat dissipation have resulted in the design of the brake disc plates being changed from a continuous rotating single plate to a plate constructed of many interconnected individual segments, with the heat dissipation properties being greatly improved, thus increasing brake efficiency. Carbon is now often used for manufacturing brake units because it has much better heat absorbing and dissipating properties than steel. This allows higher levels of braking to be maintained for longer. It also allows for quicker turnarounds, as it is not necessary to wait so long for the brakes to cool before taking off again. Carbon brakes are also much lighter than equivalent steel units. The disadvantages are their increased cost and shorter life. However, the advantages outweigh the disadvantages, and they are now found on most modern aircraft. If, in spite of all of this, the brakes become too hot, they will not be able to absorb any further energy, and their ability to slow down the aircraft rapidly diminishes. This phenomenon is termed brake fade. Each brake unit is fitted with brake adjusters, which use springs to move the pressure plate back when the brakes are released, allowing the stator and rotor assemblies to move slightly apart. The internal construction of the brake adjuster assemblies allows them to maintain a constant running clearance when the brakes are off, thereby automatically compensating for brake wear. The retraction pin is connected to the pressure plate and is a tight fit in the friction bush, which is part of and moves with the guide assembly. When the brakes are released, the spring will pull the guide, the pin and the pressure plate to the left, allowing the stator and rotor assemblies to move slightly apart. When the brakes are applied, the pressure plate will pull the pin and guide assembly to the right until the guide reaches the end of its travel. If further movement is required because of pad wear, the pin will be pulled through the friction bush. When pressure is released, the spring will pull the guide, pin and pressure plate back to the left until the guide assembly once again reaches the end of its travel, thus maintaining a constant running clearance. If the return spring inside the adjuster assembly ceases to function, or if the unit is wrongly adjusted, then the brakes may not release fully. This is termed brake drag. Brake drag will generate a lot of heat and can be responsible for brake fade occurring sooner than it otherwise would, or even for a brake fire. It is important that the thickness of the brake lining material is carefully monitored. Too little brake lining material remaining may mean that the disc of a single brake system becomes excessively worn or grooved, or on a multiple disc brake, the remaining material overheats and erodes extremely quickly. On multiple disc brake systems, the most popular method of gauging the depth of brake lining material remaining is by checking the amount that the retraction pin, or the wear indicator pin, as it is sometimes called, extends from the spring housing with the brake selected on. The minimum amount that the pin can extend beyond the housing for the brakes to remain in service will be laid down by the manufacturer. On systems where the retraction pin is located inside the housing, a wear gauge can be used to check the distance that the pin has moved within the housing. The wear gauge is held against the housing and the rod is screwed in until it touches the retraction pin. The maximum distance that the rod is permitted to extend will once again be laid down by the manufacturer. An alternative method which can be used, if no retraction pins are fitted to the system, is that, if it is accessible, the amount of clearance between the back of the pressure plate and the brake housing can be measured, again with the brakes applied. The main points to be taken from this lesson are that aircraft brake systems are normally hydraulically operated and the discs are manufactured from either steel or carbon. Carbon brakes are more efficient and heat up less than steel. However, they are more expensive and wear more quickly. You should understand the problem of brake fade. And finally, you should understand the function of automatic brake wear adjusters and the methods used for indicating wear.